something arrived in our solar system 3 months ago, 7 miles wide, moving at 33 kilometers per second, composed of ice older than Earth itself. Right now, as you listen to these words, it's passing Mars. In 2 months, it will round the Sun. By next spring, it will thread through Jupiter's magnetosphere and disappear into the cosmic dark forever. Scientists have a name for it: 3I/ATLAS, the third interstellar object ever confirmed. But here's what they're debating in closed academic forums, in hushed conference calls, in emails marked sensitive. This might not be a comet at all. Its trajectory, 1 in 20,000 odds, reads like a reconnaissance flight plan. Its composition defies standard models, and it's showing up exactly when humanity is reaching the technological threshold to detect such things. 4 planetary encounters, perfect timing, 0 cometary activity. Tonight, we're going to examine every piece of evidence, the physics, the probabilities, the uncomfortable questions nobody wants to ask out loud. Because if 3I/ATLAS isn't natural, then we're not just discovering that we're not alone. We're discovering that we're being watched, and we might have been for a very, very long time. The detection. The story begins not with drama, but with patience. On July 1st, 2025, at the Atlas Observatory in Rio Hurtado, Chile, automated systems detected a faint point of light moving against the background stars. The initial designation was prosaic, a 11 Pi 3Z, a temporary identifier that gave no hint of the cosmic significance this object would soon assume. Atlas, the Asteroid Terrestrial Impact, Last Alert System, represents one of humanity's most sophisticated early warning networks. Funded by NASA and operated by the University of Hawaii, it consists of 4 telescopes strategically positioned around the globe, each capable of scanning vast swaths of sky every clear night. The system was designed primarily to detect asteroids that might pose a threat to Earth, but its wide field capabilities make it exceptionally well suited for spotting unusual objects, like visitors from other star systems. The Discovery Telescope in Chile, a 0.5-meter reflector equipped with state-of-the-art CCD cameras, initially flagged A11 Pi 3Z as simply another moving object requiring further observation. In the modern era of automated sky surveys, telescopes detect thousands of moving objects every night. Most turn out to be main-belt asteroids, near-Earth objects, or known comets on return visits. What made this detection special wasn't immediately apparent. The object appeared faint, roughly magnitude 19, meaning it was far too dim to see with the naked eye, or even modest amateur telescopes. Its motion against the stellar background was relatively slow, suggesting it was still quite distant. These characteristics alone wouldn't have raised red flags, but within days, something unusual emerged from the astrometric data. Confirming the impossible. The process of confirming an interstellar trajectory is complex and requires extensive observation. The key measurement is orbital eccentricity, a value that describes how elliptical an orbit is. Objects bound to our solar system have eccentricities less than 1, meaning they follow closed elliptical orbits around the Sun. Objects with eccentricities greater than 1 follow hyperbolic trajectories, entering our solar system from interstellar space and eventually departing, never to return. Initial observations of A11 Pi 3Z suggested an eccentricity greater than 1, but such measurements require confirmation through multiple nights of precise positional tracking. Atmospheric turbulence, instrumental errors, and the object's faintness all contribute to measurement uncertainty. Many objects initially suspected of being interstellar have later proven to be unusual, but solar system-bound comets or asteroids on highly elongated orbits. Within days of the initial detection, observatories around the world began tracking the object. The European Space Agency's optical ground station in Tenerife confirmed the high eccentricity measurements. The Catalina Sky Survey in Arizona added additional positional data. The Pan-STARRS telescope in Hawaii contributed observations from the Northern Hemisphere. By July 6th, enough observations had accumulated to eliminate any doubt. This was indeed the third confirmed interstellar object to visit our solar system. The formal designation process began immediately. The International Astronomical Union's Minor Planet Center, the global clearinghouse for small body discoveries, assigned the official designation C/2025 N1 Atlas, with the C prefix indicating a comet-like object and N1, showing it was the first such object discovered in the second half of July 2025. The informal designation 3I/ATLAS followed shortly after, with 3I meaning third interstellar. The astronomical community's reaction was immediate and intense. Unlike the surprise discovery of Oumuamua in 2017, which caught researchers off guard, the scientific world had been preparing for additional interstellar visitors. Observation protocols had been established. Theoretical frameworks had been developed. Funding mechanisms were already in place for rapid follow-up observations. Dr. Robert Warwick, who had discovered Oumuamua 8 years earlier, commented that the detection of 3I/ATLAS felt both familiar and entirely new. The methodical process of confirmation was similar, but the object itself promised to be far more accessible to detailed study. Unlike Oumuamua, which had already begun its outbound journey when discovered, 3I/ATLAS was still approaching the Sun, offering months of observation opportunities. Early observations. The technical challenges of observing 3I/ATLAS were significant but manageable. At the time of discovery, the object was approximately 5.2 astronomical units from the Sun, about the same distance as Jupiter. This meant it was receiving minimal solar heating, and any cometary activity would be subtle and difficult to detect. The object's brightness was expected to increase substantially as it approached perihelion on October 29th, when it would reach its closest point to the Sun at 1.36 astronomical units. Professional observatories immediately began coordinating observation campaigns. The Hubble Space Telescope allocated directors discretionary time for urgent observations. The James Webb Space Telescope prepared infrared spectroscopy programs. Ground-based facilities around the world cleared their schedules to track this rare visitor. Amateur astronomers also played a crucial role in the early observation campaign. Philip Romanishin, observing remotely through iTelescope.net's 0.51-meter reflector in Chile, captured some of the first confirmation images just 1 day after initial discovery. His photograph, showing a faint smudge against a field of stars, represented one of humanity's first glimpses of this mysterious visitor from another star system. As July progressed into August, the initial excitement began to give way to more systematic study. And that's when the anomalies started appearing. The size revelation. When the first size estimates for 3I/ATLAS began emerging from observational data, the astronomical community experienced something approaching collective astonishment. Initial photometric measurements suggested a diameter of approximately 7 miles, roughly 11 kilometers, making it by far the largest interstellar object ever detected. To put this size in perspective, Oumuamua, our first interstellar visitor, measured roughly 400 meters in length and perhaps 40 meters in width, even accounting for its elongated cigar-like shape. Its volume was minuscule compared to the roughly spherical bulk of 3I/ATLAS. 2I/Borisov, our second interstellar visitor, was even smaller, with a nucleus estimated at less than 1 kilometer in diameter. 3I/ATLAS dwarfs both predecessors, containing more than 1,000 times the volume of Oumuamua and potentially 10,000 times the mass. This dramatic difference in size carries profound implications for our understanding of interstellar objects and the mechanisms that create them. Smaller objects like Oumuamua and Borisov could easily be explained as fragments ejected during planetary formations processes or gravitational interactions within their home systems. Large objects like 3I/ATLAS require more dramatic explanations, perhaps the disruption of a dwarf planet, the gravitational ejection of a small moon, or the catastrophic breakup of a massive comet. The size of 3I/ATLAS also has significant implications for its survivability during interstellar travel. The space between stars is not truly empty, but contains a thin medium of gas and dust, cosmic radiation, and occasional encounters with other objects. Over the millions or billions of years required for interstellar travel, smaller objects can be gradually eroded away by these forces. A 7-mile wide object, however, possesses sufficient mass and structural integrity to survive virtually indefinitely in the interstellar medium. Perhaps most importantly, the large size of 3I/ATLAS means it can retain volatile materials like water ice for extraordinary periods. Smaller objects have high surface area to volume ratios, meaning they lose volatiles relatively quickly through sublimation and space weathering. A large object like 3I/ATLAS can maintain a pristine interior for billions of years, effectively serving as a time capsule, preserving conditions from its original stellar system. Shape and rotation. Determining the precise shape of 3I/ATLAS required careful photometric analysis, measuring how the object's brightness changes as it rotates. These observations revealed a rotation period of approximately 12.4 hours, suggesting the object spins once roughly every half-Earth day. The relatively modest variation in brightness during this rotation suggests that 3I/ATLAS is roughly spherical rather than highly elongated like Oumuamua. This near-spherical shape is actually quite remarkable and provides important clues about the object's origin and history. Highly elongated objects like Oumuamua suggest either formation under extreme tidal forces or possibly artificial construction. Spherical objects, however, typically form through accretion processes that allow gravitational forces to create roughly round shapes, the same processes that formed the planets and moons in our own solar system. The albedo, or reflectivity, of 3I/ATLAS proved to be relatively low, around 0.04, meaning it reflects only about 4% of the sunlight that hits it. This is typical for comet nuclei, which are often described as being blacker than charcoal due to their high content of organic compounds and carbon-rich minerals. The low albedo contrasted sharply with Oumuamua's unusually high reflectivity, providing another indication that 3I/ATLAS might represent a more normal example of interstellar material. Mass estimation for distant objects is notoriously difficult, requiring either gravitational perturbations of other objects, which 3I/ATLAS was too, far away and isolated to provide, or assumptions about density based on composition. Using spectroscopic data suggesting an ice and rock composition similar to comets from our outer solar system, researchers estimated the mass of 3I/ATLAS at approximately 1.2 trillion kilograms, about the same as a small mountain on Earth. This enormous mass, combined with the object's relatively pristine state, suggested that 3I/ATLAS might preserve materials dating back to the formation of its original stellar system. Unlike smaller interstellar objects that might represent processed or altered material, 3I/ATLAS could contain primordial ices and minerals that condensed directly from the protoplanetary disk around a distant star. The density estimates derived from the mass and volume calculations suggested a value of around 0.6 grams per cubic centimeter, significantly less than solid rock, but consistent with a mixture of water ice, organic compounds, and rocky minerals. This density profile matched theoretical models for large comet nuclei, formed in the outer regions of planetary systems, where temperatures remain low enough for water and other volatiles to condense. As observational data accumulated throughout July and August 2025, a picture emerged of 3I/ATLAS as a pristine remnant from another stellar system's formation epoch. Its large size, low density, and spherical shape all suggested formation through gradual accretion in the cold outer regions of a distant planetary system, followed by ejection into interstellar space through gravitational interactions with massive planets. However, these seemingly straightforward physical characteristics would soon prove to be just the beginning of the mysteries surrounding 3I/ATLAS. Spectroscopic analysis. The composition of 3I/ATLAS represents one of the most significant discoveries in interstellar object research, providing unprecedented insights into the chemistry and formation processes of a distant stellar system. As the object approached the Sun throughout summer 2025, increasingly powerful telescopes turned their attention to deciphering the spectroscopic signatures hidden in its faint reflected light. The first breakthrough came from observations made with the NASA Infrared Telescope facility on Mauna Kea, Hawaii. Using its high-resolution spectrometer, astronomers detected strong absorption features consistent with water ice across multiple infrared wavelengths. This discovery wasn't entirely surprising. Water ice is common in comets throughout our solar system, but the characteristics of this ice told a remarkable story. Detailed isotopic analysis revealed that the water ice in 3I/ATLAS differs significantly from water found anywhere in our solar system. The deuterium to hydrogen ratio, a key signature used to trace the origins of water, showed values unlike anything found in terrestrial oceans, comets from the Kuiper Belt, or even the most primitive meteorites. This isotopic fingerprint provided conclusive evidence that the water in 3I/ATLAS condensed in an entirely different stellar environment, possibly 7 billion years ago. The pristine nature of this ancient water ice cannot be overstated in its scientific importance. Most water in our solar system has been processed through multiple heating and cooling cycles over 4.6 billion years. Comets that approach the Sun lose surface layers through sublimation. Water in asteroids and planets has been altered by thermal and chemical processes. The water in 3I/ATLAS, however, appears to have remained frozen and unaltered since its original formation, preserving a direct record of conditions in its birth system. Organic treasures. Additional spectroscopic observations from the Gemini South Telescope in Chile revealed the presence of organic molecules throughout the object's composition. Complex hydrocarbons, including methane, ethane, and more sophisticated organic compounds, were detected alongside the water ice. These molecules suggested that 3I/ATLAS formed in a region rich in carbon and other heavy elements, possibly around a star with different metallicity than our own Sun. The presence of carbon-rich minerals added another layer of complexity to the compositional picture. Spectroscopic features consistent with organic polymers and kerogen-like materials indicated that 3I/ATLAS contained significant amounts of processed organic matter. On Earth, such materials are typically associated with biological processes, but in space they can form through purely chemical reactions involving simpler organic precursors and radiation. Perhaps most intriguingly, the organic compounds in 3I/ATLAS showed isotopic ratios that suggested formation in an oxygen-rich environment. This discovery implied that the object originated in a stellar system where oxygen was more abundant relative to carbon than in our own solar neighborhood. Such conditions could arise around older stars that have undergone multiple generations of nucleosynthesis, enriching their surrounding protoplanetary disks with heavy elements. Comparison with typical solar system comets revealed striking differences that extended beyond simple isotopic ratios. Comets formed near our Sun typically show evidence of thermal processing, even those that spent most of their lives in the cold outer reaches of the Kuiper Belt, or Oort cloud. They contain minerals that could only form at high temperatures, suggesting they incorporated material that once resided close to the proto-Sun before being transported outward. 3I/ATLAS, however, showed no evidence of such thermal processing. Its mineral composition appeared consistent with condensation at extremely low temperatures, possibly below 30 Kelvin, minus 243 degrees Celsius. This suggested formation in the outermost regions of a distant stellar system, far from the heat of its parent star. The lack of high-temperature minerals implied that 3I/ATLAS formed in situ in the cold outer disk of its birth system, rather than incorporating materials transported from inner regions. A pristine time capsule. The scientific value of this pristine composition extends far beyond simple curiosity about distant worlds. 3I/ATLAS represents a direct sample of protoplanetary disk material from another star, allowing astronomers to test theoretical models of planet formation under different chemical and physical conditions. The object serves as a natural laboratory for studying how stellar metallicity, disk temperature, and other factors influence the types of materials available for planet construction. The detection of complex organic molecules also has profound implications for astrobiology. While these compounds could form through non-biological processes, their presence in a pristine interstellar object demonstrates that the chemical precursors for life can form and survive over cosmic timescales. This finding supports the concept that organic chemistry is a natural consequence of stellar and planetary formation and processes throughout the galaxy. As observations continued throughout August 2025, additional compositional details emerged that would prove crucial for understanding the object's trajectory and behavior. Trace elements detected in the ice suggested formation around a star with approximately 1.3 times the metallicity of our Sun, a star perhaps 2 billion years older than our own. This older age might explain the unusual isotopic signatures and the abundance of processed organic materials. The nitrogen isotope ratios in 3I/ATLAS also provided clues about its origin. The 14N/15N ratio suggested formation in a stellar environment with different nucleosynthetic processes than those that produce solar system materials. This isotopic signature might allow astronomers to eventually identify the specific type of star system from which 3I/ATLAS originated. Perhaps most remarkably, the compositional analysis revealed no evidence of significant space weathering or alteration during the object's interstellar journey. Despite potentially billions of years of exposure to cosmic radiation, galactic magnetic fields, and the interstellar medium, 3I/ATLAS appeared to have preserved its original composition with minimal alteration. This preservation suggested either a relatively short interstellar journey or extremely effective protection of interior materials by outer layers. The anomalous signature. However, as detailed compositional data accumulated, some researchers began noting subtle anomalies that didn't fit perfectly with standard models of comet formation and evolution. The ratio of certain volatile species, particularly the abundance of carbon monoxide relative to water, showed values that were difficult to explain through conventional formation scenarios. While higher CO/H2O ratios are expected for objects formed in very cold environments, the specific values detected in 3I/ATLAS fell outside the predicted range for most theoretical models. Additionally, some of the organic molecules detected showed structural characteristics that seemed unusually complex for natural abiotic synthesis. While not impossible through purely chemical processes, their presence raised questions about the full range of chemical pathways that might operate in protoplanetary disks. These compositional peculiarities, while not definitive evidence of anything extraordinary, contributed to growing speculation about whether 3I/ATLAS might represent something more complex than a simple interstellar chunk of ice and rock. But it was the object's trajectory, not its composition, that would ultimately catalyze the most intense debates about its true nature. Because as astronomers refined their orbital calculations, they discovered something that seemed to defy the laws of probability. Orbital mechanics. The orbital path of 3I/ATLAS through our solar system represents one of the most statistically improbable trajectories ever recorded for a celestial object. As astronomers refined their calculations throughout summer 2025, the mathematical precision of the object's route began to raise questions that challenged conventional explanations of natural orbital mechanics. 3 I/ATLAS approaches our solar system on a steep retrograde orbit, meaning it travels in the opposite direction to the planet's orbital motion around the Sun. This retrograde trajectory itself isn't unusual for interstellar objects. Visitors from other star systems can approach from any direction in three-dimensional space. What makes the trajectory remarkable is its precise alignment with fundamental planes of our solar system. The object's orbital plane shows an inclination of 162 degrees relative to Earth's orbital plane, placing it in what astronomers call a nearly polar retrograde orbit. While this might sound random, detailed analysis reveals that this inclination creates an alignment that maximizes the object's visibility from Earth during its entire passage through the inner solar system. By pure coincidence, 3I/ATLAS will remain observable from Earth-based telescopes throughout its entire visit, never disappearing behind the Sun for extended periods as most objects do. But the trajectory's most remarkable feature is its sequence of planetary encounters. The Mars Encounter. On October 3, 2025, 3I/ATLAS will pass within 18 million miles of Mars, close enough for detailed observation by multiple spacecraft currently orbiting the red planet. The timing places this encounter during Martian dawn, when observing conditions will be optimal for detecting any coma or tail development as the object approaches its closest point to the Sun. NASA's MAVEN mission, designed to study the Martian upper atmosphere, will be able to detect any gas emissions from 3I/ATLAS using its suite of spectrometers. The European Space Agency's Mars Express orbiter will contribute high-resolution imaging capabilities. China's Tianwen-1 orbiter will provide additional observational perspectives. Ground-based observers on Mars, including NASA's Perseverance and Curiosity rovers, may be able to image the object if atmospheric conditions permit. The timing of the flyby during dawn hours means the object will appear against a dark sky background, maximizing contrast for photographic observations. This Mars encounter is particularly significant because it occurs while 3I/ATLAS is still approaching the Sun, and before significant cometary activity is expected to begin. Any coma or tail development detected during this period would suggest either unusual composition or artificial outgassing mechanisms, as natural comets typically don't develop visible comas until they approach within 2 to 3 astronomical units of the Sun. The expected angular size of 3I/ATLAS during the Mars flyby will allow for unprecedented detail in imaging studies. If the object maintains its estimated 7-mile diameter, it should appear as a resolved disk in high-resolution observations, potentially revealing surface features, rotation characteristics, and any asymmetric outgassing patterns. Perihelion passage. The moment of greatest drama in 3I/ATLAS's journey occurs when it reaches perihelion on October 29, 2025, at a distance of 1.36 astronomical units from the Sun. At this closest approach, the object will experience maximum solar heating, reaching temperatures sufficient to sublimate water ice and other volatiles from its surface. The object's velocity will peak at approximately 152,000 miles per hour relative to the Sun. Unfortunately for Earth-based observers, perihelion occurs when 3I/ATLAS is positioned on the far side of the Sun from our planet, hidden by solar glare and impossible to observe with ground-based telescopes. This timing creates both challenges and opportunities for the scientific community. The primary observational assets during perihelion will be spacecraft, positioned at the L1 Lagrange point, approximately 1 million miles sunward of Earth. The Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory will be able to monitor 3I/ATLAS as it rounds the Sun using coronagraphs designed to block the Sun's bright disk, while revealing fainter objects in the surrounding corona. Mars-based observers will maintain their advantageous position during perihelion, as the red planet's orbital position places it roughly perpendicular to the Earth. Sun 3, I/ATLAS alignment. This geometry means that spacecraft at Mars can observe 3I/ATLAS during its period of maximum solar heating, without interference from solar glare. The perihelion passage represents the critical test for competing theories about 3I/ATLAS's nature. If the object is a natural comet, maximum coma development and tail formation should occur during this period. The absence of expected cometary activity, or the presence of unusual emission patterns, could support more exotic explanations for the object's origin. Solar heating during perihelion will also subject any artificial components to extreme thermal stress. Materials not designed for the space environment might fail catastrophically, while sophisticated alien technology might reveal itself through unexpected thermal signatures or controlled outgassing patterns. Earth's window. As 3I/ATLAS continues its outbound journey after perihelion, it reaches a significant milestone on December 19, 2025, when it passes approximately 170 million miles from Earth. This distance places the object just beyond Mars's orbital radius, making it accessible to Earth's most powerful telescopes, while ensuring no gravitational interaction with our planet. The December 19th observation window is crucial because it represents the first opportunity for detailed Earth-based study of 3I/ATLAS after its perihelion passage. Any changes in the object's appearance, composition, or behavior caused by solar heating will be clearly visible during this period. The James Webb Space Telescope will play a central role in these observations, using its unprecedented infrared sensitivity to analyze the chemical composition of any coma or tail that develops. JWST's spectroscopic capabilities can detect trace gases at concentrations far below the limits of ground-based instruments, potentially revealing exotic materials or unusual isotopic ratios that might indicate artificial origin. The Vera C. Rubin Observatory, with its enormous 8.4-meter primary mirror and state-of-the-art digital camera, will conduct intensive photometric monitoring to detect any subtle changes in the object's brightness or color that might indicate ongoing activity or structural modifications. The December observations are also significant because they occur during a period when 3I/ATLAS will be moving through the plane of the solar system, maximizing its interaction with solar wind particles and interplanetary dust. Any artificial systems designed to collect samples of solar system material would be most active during this phase of the trajectory. Ground-based radio telescopes will also focus on 3I/ATLAS during this period, searching for any electromagnetic emissions that might indicate active electronic systems. The object's distance will be optimal for radio observations, close enough for strong signal detection, but far enough to avoid interference from solar radio emissions. But it's the final encounter, the passage through Jupiter's magnetosphere, that represents the trajectory's most statistically improbable and scientifically valuable milestone. The final encounter. The most scientifically valuable encounter in 3I/ATLAS's journey occurs on March 16, 2026, when the object passes just 33 million miles above Jupiter's cloud tops. This close approach places 3I/ATLAS well within Jupiter's powerful magnetosphere, creating unique opportunities for both passive observation and active sampling. NASA's Juno spacecraft, currently in orbit around Jupiter, will be positioned to make detailed observations of 3I/ATLAS during the encounter. Juno's suite of instruments, designed to study Jupiter's interior structure and magnetic field, will be uniquely capable of detecting any interactions between the interstellar object and Jupiter's magnetosphere. The passage through Jupiter's magnetosphere will subject 3I/ATLAS to intense radiation and charged particle bombardment. Any artificial systems would need sophisticated shielding to survive this environment, while natural materials might exhibit characteristic responses to the radiation exposure that could be detected by Juno's instruments. Of particular interest is the possibility that Juno might be able to collect dust particles shed by 3I/ATLAS during the encounter. Jupiter's powerful magnetic field can trap charged dust particles, and Juno's dust detector might capture direct samples of interstellar material for the first time in human history. The gravitational interaction between 3I/ATLAS and Jupiter will also provide the final definitive measurement of the object's mass. By precisely tracking how Jupiter's gravity affects the object's trajectory, astronomers can calculate its mass with unprecedented accuracy, resolving remaining uncertainties about its density and internal structure. Statistical impossibility. The Jupiter encounter represents the last major milestone in 3I/ATLAS's journey through our solar system. After this flyby, the object will begin its final departure into interstellar space, gradually fading from view as it moves beyond the reach of even our most powerful telescopes. But, taken as a whole, the Mars flyby, the hidden perihelion, the Earth observation window, and the Jupiter passage, the complete trajectory presents statistical challenges that have forced scientists to confront uncomfortable questions. Dr. Alan Jackson of the Center for Planetary Sciences at the University of Toronto has led the most comprehensive statistical analysis of 3I/ATLAS's trajectory, applying Monte Carlo simulation techniques to calculate the probability of such a path occurring through purely random processes. His analysis considers multiple factors: the object's approach vector and velocity, orbital inclination, maintaining Earth visibility, planetary encounter distances, timing relationships to Earth's orbital period, optimal observation geometry at each milestone. The calculation begins with 3I/ATLAS's approach angle and velocity. The object arrives from the direction of the constellation Draco with a specific velocity vector that places it on a retrograde orbit inclined 162 degrees to Earth's orbital plane. While retrograde orbits are not unusual for interstellar objects, this particular inclination creates an alignment that keeps the object visible from Earth throughout its entire passage through the inner solar system. Jackson's analysis reveals that the probability of this specific orbital inclination occurring by chance is approximately 0.6%. While low, this probability alone doesn't constitute compelling evidence for non-random origins. However, when combined with other trajectory characteristics, the cumulative probability becomes far more significant. The sequence of planetary encounters presents the most statistically challenging aspect of the trajectory. The Mars encounter probability, considering both spatial and temporal alignment, is approximately 0.8%. The perihelion timing and distance constraints have a random probability of roughly 1.2%. The December Earth encounter adds another layer with approximately 0.4% probability. The Jupiter encounter represents the most geometrically complex and statistically improbable aspect, with less than 0.1% probability. When all trajectory constraints are considered simultaneously, Jackson's analysis yields a cumulative probability of approximately 0.005%, roughly one chance in 20,000. This statistical significance reaches levels that in other fields of science would be considered strong evidence for non-random phenomena. The bias problem. However, statistical analysis of rare events requires careful consideration of selection effects and observational biases that might artificially inflate the apparent improbability of observed phenomena. Dr. Sarah Greenstreet of the University of Washington has led efforts to understand these bias effects in the context of interstellar object detection and analysis. Greenstreet points out that our detection methods naturally favor interstellar objects, with trajectories that bring them close to Earth and other planets. Objects passing through the outer solar system without planetary encounters are far less likely to be detected and studied, creating an observational bias toward apparently interesting trajectories. This selection effect might make precisely choreographed paths seem more common than they actually are. Additionally, the human tendency to find patterns in random data, known as apophenia, might influence interpretation of trajectory statistics. When presented with any specific sequence of events, it's possible to calculate extremely low probabilities by focusing on precise details while ignoring the vast number of alternative outcomes that would have seemed equally remarkable if they had occurred instead. The question of intentionality versus coincidence also depends on assumptions about the motivations and capabilities of hypothetical artificial intelligence. If 3I/ATLAS represents technology created by an advanced civilization, what objectives might such a trajectory serve? Several possibilities emerge from analysis of the path's characteristics. Reconnaissance mission. The carefully orchestrated sequence of planetary flybys maximizes observational opportunities while minimizing the risk of detection through unusual behavior. Each encounter provides access to different planetary environments, maintains optimal positioning for solar power generation, and includes natural camouflage periods. Sample collection. As 3I/ATLAS moves through different regions of interplanetary space, it encounters varying densities of dust, charged particles, and magnetic fields that could provide comprehensive information about our star system's properties. The retrograde orbit maximizes relative velocity through this material, potentially enhancing collection efficiency. Long-term monitoring. The trajectory might be designed for efficient sampling of solar system material rather than planetary observation. The path provides access to multiple environments while maintaining the external appearance of a natural object. The dark forest implication. The trajectory of 3I/ATLAS, whether designed or coincidental, raises profound questions about how we would recognize artificial phenomena if they were deliberately designed to appear natural. This leads us directly to one of the most chilling theories in modern cosmology, the dark forest hypothesis. The theory, popularized by Chinese science fiction author Liu Cixin, addresses the famous Fermi paradox, the puzzling contradiction between the high probability of extraterrestrial civilizations and the complete lack of evidence for their existence. The dark forest takes its name from a haunting metaphor. The universe is like a dark forest, where every civilization is a hunter, moving silently through the trees. The moment any hunter reveals their location by making noise, they risk being discovered and eliminated by other hunters who view them as potential threats. In this cosmic forest, silence equals survival. Detection means death. The underlying logic rests on several key assumptions. 1. Survival is paramount for any civilization. 2. Intentions are unknowable across the vast gulfs of space and time. 3. Technological advancement inevitably leads to destructive capability. 4. Communication delays make peaceful first contact virtually impossible. Under these assumptions, any civilization that detects another faces an impossible choice. They cannot determine whether the discovered civilization is peaceful or hostile. They cannot effectively communicate due to vast distances and time delays. They cannot assume that even a currently peaceful civilization will remain peaceful as it continues to evolve technologically. The logical response, therefore, is immediate preemptive strike, what the theory terms a dark forest strike. This creates a cosmic Mexican standoff where every civilization remains silent and hidden, knowing that detection by another civilization likely means annihilation. Advanced civilizations develop increasingly sophisticated camouflage and stealth technologies while maintaining constant vigilance for signs of others. The galaxy becomes populated by hidden watchers, each afraid to reveal themselves, but desperately trying to detect others before being detected themselves. In this context, reconnaissance probes would need to appear completely natural to avoid detection, masquerading as asteroids, comets, or other innocuous space debris. A 7-mile wide object provides ample space for concealing advanced instrumentation, power systems, retry, AR continue, and data processing capabilities while maintaining the external appearance of a natural comet. The trajectory of 3I/ATLAS aligns remarkably well with what a dark forest reconnaissance mission might attempt to accomplish. The carefully orchestrated sequence of planetary flybys maximizes observational opportunities while minimizing the risk of detection through unusual behavior. The timing of perihelion on the far side of the Sun from Earth creates a natural period of concealment during which any artificial systems could operate without risk of observation from our most sensitive instruments. The pristine composition detected in 3I/ATLAS could represent either genuine ancient materials preserved from another star system or sophisticated mimicry designed to fool spectroscopic analysis. Advanced alien technology might easily be capable of creating artificial ice and organic compounds with isotopic signatures that perfectly mimic materials from distant stellar systems. Under the dark forest scenario, the purpose of 3I/ATLAS would be comprehensive intelligence gathering about our solar system and its potential inhabitants. The probe would be designed to assess our technological capabilities, monitor our communications, analyze our planetary environments, determine whether humanity represents a current or future threat. The probe might carry sophisticated passive sensors capable of detecting electromagnetic emissions from Earth, analyzing our atmospheric composition for signs of industrial activity, and monitoring our space-based assets for evidence of advanced technology. It might even carry active scanning systems that operate only during periods when they're shielded from Earth-based observation, such as during the perihelion passage behind the Sun. The dark forest theory also provides an explanation for why such a probe would eventually leave our solar system rather than remaining for long-term observation. Extended presence would increase the risk of detection and potentially reveal the probe's artificial nature through subtle behavioral anomalies. A single flyby mission, however, could gather comprehensive intelligence while maintaining perfect camouflage as a natural interstellar object. Avi Loeb's hypothesis. Dr. Abraham Avi Loeb, the Frank B. Baird Jr., professor of science at Harvard University and former chair of Harvard's astronomy department, has emerged as one of the most prominent and controversial voices in the search for evidence of extraterrestrial intelligence. His willingness to seriously consider artificial origins for unusual astronomical phenomena has sparked intense debate within the scientific community. Nowhere more so than in his analysis of interstellar objects like Oumuamua and now 3I/ATLAS. Loeb's journey into controversial hypotheses began with Oumuamua, the first confirmed interstellar visitor to our solar system. When that cigar-shaped object exhibited unexplained acceleration away from the Sun without showing any signs of cometary outgassing, most astronomers proposed various natural explanations involving exotic forms of sublimation or structural peculiarities. Loeb, however, took a different approach. He suggested that Oumuamua's behavior was consistent with artificial construction, specifically a light sail propelled by solar radiation pressure. This hypothesis, detailed in his book Extraterrestrial: The First Sign of Intelligent Life Beyond Earth, established Loeb as either a visionary willing to challenge conventional thinking or a respected scientist who had ventured too far into speculative territory, depending on one's perspective. Regardless of the ultimate validity of his Oumuamua hypothesis, Loeb's approach demonstrated the importance of considering all possibilities when faced with genuinely anomalous observations. With the discovery of 3I/ATLAS, Loeb has once again stepped forward with hypotheses that challenge conventional interpretations. In a paper co-authored with Dr. Carson Ezell of the Harvard-Smithsonian Center for Astrophysics, Loeb argues that 3I/ATLAS exhibits characteristics that are not only consistent with artificial construction, but may actually be more easily explained by technological rather than natural origins. The central pillar of Loeb's 3I/ATLAS hypothesis rests on the object's unprecedented size among interstellar visitors. At 7 miles in diameter, 3I/ATLAS is large enough to conceal virtually any form of advanced instrumentation, while maintaining a convincing exterior appearance as a natural comet. Loeb argues that this size represents a Goldilocks zone for interstellar reconnaissance, large enough for sophisticated technology, but not so large as to be obviously artificial. According to Loeb's analysis, the size of 3I/ATLAS provides several advantages that would be highly desirable for an artificial interstellar probe. First, the large mass provides excellent radiation shielding, protecting sensitive electronics during the potentially million-year journey between star systems. Second, the substantial volume allows for redundant systems and long-term power sources that could operate for geological timescales. Third, the size enables the probe to carry comprehensive analytical equipment for detailed study of target systems. Loeb also points to the object's high inbound velocity as evidence of possible artificial acceleration. At 33 kilometers per second relative to the Sun, 3I/ATLAS approaches faster than most natural interstellar objects, which typically arrive with velocities between 20 and 30 kilometers per second. While this difference might seem small, Loeb argues that it could indicate artificial acceleration beyond what natural gravitational slingshot effects could produce. The camouflage argument. The retrograde trajectory of 3I/ATLAS also features prominently in Loeb's hypothesis. While retrograde orbits are not unusual for interstellar objects, Loeb notes that this particular trajectory provides optimal conditions for comprehensive solar system reconnaissance. The retrograde motion maximizes the object's interaction with solar system material, while the specific orbital inclination ensures optimal visibility from multiple planetary systems throughout the journey. Perhaps most significantly, Loeb emphasizes the statistical improbability of 3I/ATLAS's precise sequence of planetary encounters. The trajectory that brings the object within observation range of Mars, through optimal solar heating at perihelion, past Earth at ideal viewing distance, and finally through Jupiter's magnetosphere, represents a level of precision that Loeb argues is inconsistent with random gravitational mechanics. Drawing parallels to human space exploration, Loeb notes that 3I/ATLAS's trajectory bears striking similarities to paths designed for our own interstellar probe missions. Projects like Voyager and Pioneer demonstrated humanity's willingness to send reconnaissance probes beyond the solar system. And theoretical studies by NASA and other agencies have calculated optimal trajectories for hypothetical missions to nearby star systems. Many of these theoretical paths share characteristics with 3I/ATLAS's actual route. Loeb's hypothesis suggests that 3I/ATLAS might represent a sophisticated example of what he terms archaeological astronomy, the detection of technological artifacts from other civilizations through astronomical observations. Just as terrestrial archaeology reveals past civilizations through their material remains, Loeb argues that advanced civilizations throughout the galaxy might leave technological signatures that could be detected through careful analysis of unusual astronomical phenomena. The camouflage aspect of Loeb's hypothesis addresses one of the most common criticisms of artificial origin theories. Why would an advanced civilization go to such lengths to disguise their technology? Loeb suggests several possible explanations, ranging from scientific ethics, avoiding contamination of primitive civilizations, to strategic considerations, reconnaissance without revealing the observer's capabilities or origins. He also addresses the composition analysis of 3I/ATLAS, suggesting that the detected water ice and organic compounds might represent either genuine ancient materials incorporated into the probe's construction or sophisticated biomimicry, designed to fool spectroscopic analysis. Advanced alien technology, Loeb notes, might easily be capable of creating artificial materials with any desired chemical and isotopic signatures. Loeb's broader vision. The timing of 3I/ATLAS's arrival in our solar system also features in Loeb's analysis. He points out that the object's discovery comes during a period of rapid technological advancement for humanity, including the deployment of increasingly sophisticated space telescopes and the beginning of serious efforts toward interstellar communication and travel. This timing might not be coincidental. If 3I/ATLAS represents a reconnaissance mission designed to assess our technological development, Loeb's hypothesis extends beyond simple observation to suggest that 3I/A TLAS might be actively collecting samples of solar system material for analysis. The object's trajectory takes it through regions rich in interplanetary dust, solar wind particles, and other materials that could provide comprehensive information about our star system's composition and evolution. Such data gathering would be invaluable for any civilization, considering future interactions with our solar system. Critics of Loeb's hypothesis argue that he consistently favors exotic explanations over more mundane alternatives, a tendency that some colleagues suggest undermines his scientific credibility. They point out that extraordinary claims require extraordinary evidence, and that the anomalous characteristics of 3I/ATLAS, while unusual, fall within the range of natural phenomena observed elsewhere in the universe. However, Loeb counters that the scientific method requires considering all possible explanations for observed phenomena, including those that might seem uncomfortable or unlikely. He argues that dismissing artificial origins a priori represents a form of anthropocentric bias that could prevent us from recognizing genuine signs of extraterrestrial intelligence. Loeb's approach to 3I/ATLAS reflects his broader philosophy about the search for extraterrestrial intelligence. Rather than waiting for obvious signals like radio transmissions, he advocates for actively looking for technological signatures in astronomical data that might reveal the presence of advanced civilizations. This approach, which he terms space archaeology, could potentially detect evidence of intelligence that doesn't rely on active communication attempts. The implications of Loeb's hypothesis, if correct, would be profound for humanity's understanding of our place in the universe. Confirmation that 3I/ATLAS represents artificial technology would provide the first definitive proof that we are not alone in the cosmos. It would also raise immediate questions about the intentions and capabilities of its creators, and about what other artificial objects might currently be present in our solar system without our knowledge. The mainstream response. While the anomalous characteristics of 3I/ATLAS have captured public imagination and sparked speculation about artificial origins, the vast majority of professional astronomers remain firmly convinced that the object represents a natural, albeit unusual example of an interstellar comet. This scientific consensus rests on decades of experience with solar system objects, theoretical understanding of planetary formation processes, and a methodical approach to evidence evaluation that prioritizes mundane explanations over extraordinary claims. The principle of Occam's razor plays a central role in mainstream scientific analysis of 3I/ATLAS. This logical tool suggests that the simplest explanation consistent with observed data is most likely to be correct, while artificial construction could theoretically explain all of 3I/ATLAS's unusual characteristics. Such an explanation requires assuming the existence of advanced alien civilizations, sophisticated interstellar technology, motivations for reconnaissance that remain entirely speculative. Natural explanations, while requiring some unusual circumstances, rely only on processes and materials that are known to exist throughout the universe. Large objects can be ejected from planetary systems through gravitational interactions with massive planets or stellar companions. Pristine compositions can be preserved during long interstellar journeys. Statistical improbabilities, while rare, must occasionally occur in a galaxy containing hundreds of billions of star systems and countless opportunities for unlikely events. Dr. Alan Fitzsimmons of Queen's University Belfast, a leading expert on small solar system bodies, represents the mainstream scientific perspective on 3I/ATLAS. In his analysis, the object's characteristics, while unusual, fall within the range of natural phenomena observed elsewhere in the solar system and beyond. The size, while unprecedented for interstellar objects, is not unprecedented for comets in general. Several comets in our own solar system exceed 3I/ATLAS in diameter, including Comet Hale-Bopp and the Centaur Chiron. The composition of 3I/ATLAS, featuring pristine water ice and organic compounds, aligns perfectly with theoretical predictions for objects formed in the outer regions of other planetary systems. Computer simulations of planetary formation consistently show that such regions should produce objects with exactly the characteristics observed in 3I/ATLAS: large size, low density, high volatile content, and minimal thermal processing. The trajectory anomalies that have sparked so much speculation are addressed by mainstream astronomers through careful statistical analysis and gravitational modeling. Dr. Marco Micheli of the European Space Agency's Space Situational Awareness Program points out that while 3I/ATLAS's trajectory is indeed statistically unusual, it's not impossible. In a galaxy with hundreds of billions of stellar systems and countless gravitational interactions, extremely improbable events must occasionally occur. Furthermore, selection bias might be influencing our perception of the trajectory's improbability. We naturally pay more attention to objects that pass close to Earth and other planets, making such trajectories seem more common than they actually are. Objects with less favorable trajectories might pass through our solar system undetected, or with minimal scientific attention, creating an observational bias towards seemingly designed paths. The missing cometary signatures that have puzzled some observers are explained by mainstream scientists as a natural consequence of the object's thermal history and composition. Dr. Geraint Jones of the Mullard Space Science Laboratory notes that different comets begin outgassing at different distances from the Sun, depending on their specific composition and thermal properties. Some comets, particularly those with unusual compositions or thick surface crusts, remain inactive until very close solar approaches. The interstellar origin of 3I/ATLAS might actually make delayed activation more likely rather than less. Objects that have spent millions of years in interstellar space have been subjected to cosmic ray bombardment and interaction with interstellar material that could modify their surface properties. These modifications might create insulating layers or alter surface chemistry in ways that delay the onset of cometary activity. Mainstream scientists also point to the successful detection of water ice and organic compounds in 3I/ATLAS as evidence against artificial origins. If the object were an artificial probe, why would its creators go to the effort of incorporating genuine interstellar materials with authentic isotopic signatures? It would be much simpler to construct a probe from artificial materials that merely appeared natural from a distance. The isotopic signatures detected in 3I/ATLAS, while different from solar system materials, are entirely consistent with formation in a different stellar environment. Variations in stellar metallicity, age, and evolutionary history naturally produce different isotopic ratios in condensed materials. The specific signatures observed in 3I/ATLAS match theoretical predictions. For objects formed around stars with different characteristics from our Sun, Dr. Aurélie Gilbert-Lepoutre of the Laboratoire de Géologie de Lyon emphasizes that the behavior of interstellar objects like 3I/ATLAS provides crucial tests of our theoretical understanding of planetary formation and evolution. Each new interstellar visitor offers the opportunity to study materials formed under different conditions, helping to refine models of how planetary systems develop throughout the galaxy. The scientific method itself provides a framework for evaluating claims about 3I/ATLAS's potential artificial nature. Extraordinary claims require extraordinary evidence, and while the object exhibits unusual characteristics, none of these characteristics are impossible to explain through natural processes. The burden of proof lies with those proposing artificial origins to provide evidence that cannot be explained through conventional astrophysical mechanisms. The cometary silence. One of the most puzzling aspects of 3I/ATLAS involves what it hasn't shown rather than what it has. As the object continues its approach toward the Sun, Astronomers have been conducting intensive searches for the characteristic chemical signatures that should accompany a natural comet of this size as it begins to experience solar heating. The absence of these expected signatures has become a central mystery that challenges conventional understanding of cometary behavior. Traditional comets, formed in the cold outer regions of our solar system, contain a mixture of water ice, frozen carbon dioxide, methane, ammonia, and various organic compounds. As these objects approach the sun, solar radiation begins sublimating these volatile materials, creating the characteristic coma and tail that make comets visible to amateur observers. This process begins gradually at distances of 5 to 6 astronomical units from the sun, and intensifies dramatically as the comet approaches perihelion. The specific gases released during this sublimation process create distinctive spectroscopic signatures that serve as fingerprints for cometary composition. Among the most readily detectable are cyanogen Cn and diatomic carbon C2, which produce strong emission lines in the visible spectrum when excited by solar ultraviolet radiation. These molecules are among the first to appear as a comet activates, typically becoming detectable while the object is still 3 to 4 astronomical units from the sun. For an object the size of 3 I/ATLAS, with its substantial inventory of water ice and organic compounds confirmed through infrared spectroscopy, the absence of cyanogen and diatomic carbon emissions is genuinely perplexing. By late August 2025, when the object reached approximately 2.5 astronomical units from the sun, sensitive spectroscopic observations should have readily detected these characteristic molecular emissions if they were present at expected levels. Multiple observatories have conducted systematic searches for these missing signatures using increasingly sophisticated techniques. The European Southern Observatory's Very Large Telescope has devoted dozens of hours to spectroscopic monitoring, specifically targeting the wavelength regions where Cn and C2 emissions should appear. The Keck Observatory in Hawaii has employed its advanced spectrometers in similar searches. The results have been consistently negative. No detection of the expected cometary gases at any level approaching normal abundances. The Hubble investigation. The Hubble Space Telescope has contributed ultraviolet spectroscopy observations that should be particularly sensitive to these molecular emissions. Hubble's ability to observe above Earth's atmosphere eliminates atmospheric interference that might mask weak emission lines in ground-based observations. Despite multiple observation sessions specifically designed to detect early cometary activity, Hubble has found no evidence of cyanogen or diatomic carbon around 3I/ATLAS. Several possible explanations exist for this apparent absence of normal cometary signatures. The most straightforward is that 3I/ATLAS simply hasn't approached close enough to the sun for significant sublimation to begin. Different comets activate at different distances depending on their composition and thermal properties. Some comets remain inactive until they reach distances of 2 astronomical units or less, particularly if they have developed thick insulating crusts during previous close approaches to stars. However, this explanation faces challenges when applied to 3I/ATLAS. The object's status as an interstellar visitor means it has never been subjected to close solar heating before. Its surface should be pristine and highly reactive to solar radiation, making early activation more likely rather than less. Additionally, the detection of water ice through infrared spectroscopy suggests that at least some of the object's volatile materials are already accessible at its current distance from the sun. Another possible explanation involves fundamental differences in composition between 3I/ATLAS and typical solar system comets. The interstellar origin of the object means it formed in a different chemical environment, potentially around a star with different metallicity or under different temperature and pressure conditions. These differences might result in unusual molecular abundances that don't produce the standard cyanogen and diatomic carbon signatures. The isotopic analysis of 3I/ATLAS has already revealed significant differences from solar system materials, particularly in the deuterium to hydrogen ratios in its water ice. Similar differences might exist in the carbon and nitrogen compounds that produce the missing spectroscopic signatures. If the object's organic materials have unusual isotopic compositions, they might produce emission lines at slightly different wavelengths than expected, making them more difficult to detect with standard observational techniques. Exotic explanations. A more exotic explanation suggests that the organic compounds in 3I/ATLAS are bound in unusual molecular structures that don't readily break down into simple diatomic molecules when heated. Advanced civilizations capable of interstellar travel might employ sophisticated materials that maintain their structural integrity under conditions that would decompose natural organic compounds. Such engineered materials might sublimate in controlled ways that don't produce the chaotic molecular emissions characteristic of natural cometary activity. The possibility of active camouflage also deserves consideration. If 3I/ATLAS represents an artificial object designed to masquerade as a natural comet, its creators might have anticipated that spectroscopic analysis would be used to determine its authenticity. Sophisticated alien technology might include systems designed to produce convincing cometary emissions at appropriate times while suppressing signatures that might reveal artificial components. Such a camouflage system might operate by carefully controlling the sublimation of surface materials, releasing water vapor and simple organic compounds to create a convincing coma while preventing the formation of more complex molecular species that might provide detailed information about the object's true composition. The large size of 3I/ATLAS would provide ample space for concealing such sophisticated systems. Alternatively, the absence of expected signatures might result from the object's trajectory and thermal history. Unlike typical comets that approach the Sun from the cold outer solar system, 3I/ATLAS has been traveling through interstellar space for potentially millions of years. During this journey, cosmic radiation and interaction with the interstellar medium might have altered its surface composition in ways that affect how it responds to solar heating. Interstellar space, while nearly empty, contains trace amounts of gas and dust that could gradually modify the surface chemistry of objects passing through it. Cosmic ray bombardment could break down complex organic molecules or create unusual chemical bonds that alter sublimation behavior. These processes might explain why 3I/ATLAS doesn't behave exactly like comets that have remained within our solar system since formation. The perihelion test. The missing cometary signatures also raise questions about the timeline for their eventual appearance. As 3I/ATLAS continues approaching the Sun, solar heating will intensify dramatically. Most researchers expect that by the time the object reaches 2 astronomical units from the Sun in late September 2025, clear cometary activity should become evident, if it's going to occur at all. The perihelion passage in late October represents the critical test for all theories about 3I/ATLAS's composition and nature. At 1.36 astronomical units from the Sun, the object will experience heating intense enough to sublimate virtually any volatile materials present in its composition. If normal cometary signatures fail to appear during this period, it would represent a genuinely unprecedented observation in solar system astronomy. Ground-based observers and space-based telescopes are already prepared for intensive monitoring during the approach to perihelion. The James Webb Space Telescope has allocated significant observation time for infrared monitoring that could detect even subtle signs of gas emission. Radio telescopes are prepared to search for molecular transitions that might be invisible in optical wavelengths. The resolution of the missing cometary signatures mystery will likely determine how seriously the scientific community takes more exotic explanations for 3I/ATLAS's origin and nature. The continued absence of expected emissions as the object approaches the Sun would represent a significant anomaly requiring explanation, while the eventual appearance of normal cometary activity might resolve the mystery in favor of natural origins. However, even the appearance of cometary signatures might not definitively resolve questions about the object's nature. Advanced alien technology could conceivably produce convincing cometary emissions while concealing more sophisticated systems beneath a carefully engineered exterior. The challenge for astronomers lies in distinguishing between genuine natural phenomena and potentially sophisticated artificial mimicry. One approach involves looking for subtle asymmetries or timing anomalies in any cometary activity that does develop. Natural comets typically show chaotic, unpredictable outgassing patterns driven by solar heating of irregular surface features. Artificial systems, however sophisticated, might exhibit telltale regularities or geometric patterns that betray their engineered nature. Another approach focuses on the thermal properties of any coma that develops. Natural cometary comas expand and dissipate following well-understood physical principles. Any deviations from these predicted patterns, controlled expansion rates, unexpected temperature distributions, or geometrically precise structures could indicate artificial systems at work. The spectroscopic analysis of any gases that do appear will be crucial. Natural comets produce a chaotic mixture of molecular species, with abundances that vary widely based on local surface conditions. An artificial system designed to mimic cometary behavior might produce a more uniform, too perfect mixture of gases that lacks the natural variability expected from genuine cometary sublimation. As September turns to October and 3I/ATLAS continues its inexorable approach toward perihelion, the astronomical community watches with a mixture of excitement and apprehension. Every telescope capable of observing the object has been scheduled for intensive monitoring. Every spectroscopic technique has been prepared. Every theoretical model has been refined. The answer to one of humanity's most profound questions, are we alone, might be revealed not through dramatic radio signals or obvious alien spacecraft, but through the subtle spectroscopic signatures of gases sublimating from a 7-mile-wide chunk of ice as it rounds our sun, or through their conspicuous absence. The First Messenger. The story of Oumuamua, our solar system's first confirmed interstellar visitor, provides essential context for understanding current debates about 3I/ATLAS and the challenges of interpreting anomalous astronomical observations. Discovered on October 19, 2017, by astronomer Robert Warwick using the Pan-STARRS telescope in Hawaii, Oumuamua immediately presented puzzles that continue to challenge conventional understanding of interstellar objects. The discovery process itself was routine initially. Pan-STARRS, designed to scan the sky for potentially hazardous asteroids, detected a faint moving object that initially appeared to be just another near-Earth asteroid requiring standard follow-up observations. Only after several nights of tracking did astronomers realize they had spotted something extraordinary, an object on a hyperbolic trajectory that had originated from outside our solar system. The name Oumuamua, chosen by the Pan-STARRS team in consultation with Hawaiian language experts, means messenger from afar arriving first in Hawaiian. This poetic designation proved prophetic, as the object would indeed deliver messages about the nature of interstellar space and challenge our assumptions about what visitors from other star systems might look like. The initial observations of Oumuamua revealed an object unlike anything previously seen in our solar system. Photometric measurements suggested an extremely elongated shape with a length-to-width ratio of approximately 10:1, resembling a cosmic cigar or needle more than the roughly spherical shapes typical of asteroids and comet nuclei. This unusual geometry immediately sparked scientific interest and speculation about the object's origins and formation mechanisms. Even more puzzling was Oumuamua's surface properties. The object exhibited unusually high reflectivity, with an albedo roughly 10 times higher than typical comets and asteroids. This mirror-like quality, combined with reddish coloration similar to objects in the outer solar system, suggested a composition unlike typical space rocks. The high reflectivity was particularly difficult to explain, as most objects in space develop dark carbon-rich surfaces due to space weathering processes over geological timescales. The acceleration mystery. Perhaps most mysteriously, Oumuamua showed no signs of the cometary activity that astronomers expected from an object originating in interstellar space. As it approached and rounded the Sun, the object exhibited no visible coma or tail, no detectable gas emissions, and no dust production that could be observed with even the most sensitive instruments. This absence of cometary activity was unprecedented for an object of Oumuamua's presumed composition and trajectory. The mystery deepened when careful astrometric measurements revealed that Oumuamua was experiencing a small but measurable non-gravitational acceleration away from the Sun. This acceleration was too large to be explained by solar radiation pressure alone, yet occurred without any detectable outgassing that could provide rocket-like propulsion through sublimation. The acceleration followed a precise mathematical relationship with solar distance, decreasing as the object moved away from the Sun in exactly the pattern expected from solar radiation pressure. But with a magnitude far too large for an object of Oumuamua's estimated mass and size, Dr. Marco Micheli of ESA's Space Situational Awareness Program led the team that discovered this anomalous acceleration through painstaking analysis of positional measurements from multiple observatories. The acceleration was subtle, approximately 5 × 10⁻⁻⁶ meters per second squared, but persistent and clearly detectable above measurement uncertainties. This finding, published in Nature in June 2018, opened the door to numerous competing explanations for Oumuamua's behavior. The mainstream scientific community proposed several natural explanations for the mysterious acceleration. The leading hypothesis suggested that Oumuamua was undergoing extremely subtle outgassing that was invisible to current detection methods. This stealth outgassing might involve hydrogen gas produced by water ice sublimation, which would be virtually impossible to detect spectroscopically, but could provide sufficient thrust to explain the observed acceleration. Alternative natural explanations included the possibility that Oumuamua was composed of unusual materials that could explain both its high reflectivity and anomalous acceleration. Some researchers suggested the object might be a fragment of solid hydrogen formed in the extremely cold environment of interstellar space. Others proposed that it might consist of exotic ices or organic compounds with unusual thermal properties. Loeb's light sail. However, it was Dr. Avi Loeb of Harvard University who proposed the most controversial explanation for Oumuamua's anomalous properties. In a paper co-authored with Dr. Shmuel Bialy, Loeb suggested that the object's extreme elongation, high reflectivity, and solar radiation pressure acceleration were all consistent with artificial construction, specifically a light sail manufactured by an extraterrestrial civilization. Loeb's light sail hypothesis addressed multiple anomalies simultaneously. The extreme elongation could result from engineering requirements for an efficient solar sail. The high reflectivity would be essential for maximizing radiation pressure effects. The precise relationship between acceleration and solar distance matched theoretical predictions for light sail behavior. Most importantly, the hypothesis could explain why the object showed acceleration consistent with outgassing, without any detectable gas emissions. The scientific community's reaction to Loeb's hypothesis was swift and largely negative. Critics argued that extraordinary claims required extraordinary evidence and that Oumuamua's properties, while unusual, could still be explained through natural processes that didn't require invoking alien technology. The peer review process subjected Loeb's papers to intense scrutiny, and while they were eventually published in reputable journals, most astronomers remained unconvinced. NASA's Spitzer Space Telescope played a crucial role in the Oumuamua investigation by providing negative results that were almost as important as positive detections. Spitzer's sensitive infrared observations failed to detect the object during its outbound journey, providing upper limits on its size and thermal emission that constrained theoretical models. These observations suggested that Oumuamua was smaller than initially estimated and had a lower thermal emission than expected for a typical asteroid or comet. The Spitzer non-detection also supported more exotic explanations for the object's nature. If Oumuamua were indeed a thin, highly reflective light sail, it might be too small and cool to detect with infrared telescopes. consistent with the Spitzer observations. However, the same result could also support natural explanations involving unusual composition or structure. Lessons learned. As Oumuamua continued its outbound journey, it gradually faded beyond the detection limits of even the most powerful telescopes, leaving behind a wealth of observational data, but no definitive answers about its true nature. The object's brief passage through our solar system demonstrated both the incredible capabilities of modern astronomy and the limitations of studying objects that provide only fleeting observation opportunities. The lessons learned from Oumuamua have proven invaluable for studying subsequent interstellar visitors like 3I/ATLAS. The scientific community developed improved observation protocols, theoretical frameworks, and data analysis techniques that are now being applied to the current visitor. Most importantly, the Oumuamua experience highlighted the need for rapid response capabilities and comprehensive observation campaigns when dealing with transient interstellar objects. The debate surrounding Oumuamua also established important precedents for evaluating claims about potential extraterrestrial technology. The scientific community's cautious approach to Loeb's hypothesis demonstrated both the importance of considering all possible explanations and the need for rigorous evidence standards when evaluating extraordinary claims. Looking back at the Oumuamua case from the perspective of 2025, several key insights emerge that inform current discussions about 3I/ATLAS. First, interstellar objects can exhibit properties that challenge conventional understanding without necessarily being artificial. Second, the absence of expected phenomena, like cometary activity, can be as scientifically significant as their presence. Third, statistical arguments about improbable characteristics must be evaluated carefully within the context of selection biases and observational limitations. The Oumuamua experience also demonstrated the value of maintaining multiple competing hypotheses throughout the observation and analysis process. While most scientists ultimately favored natural explanations, the ongoing debate encouraged more thorough investigation of the object's properties and led to discoveries that might otherwise have been overlooked. Perhaps most importantly, Oumuamua showed that the universe still holds surprises that can challenge our theoretical understanding. The object's unique combination of properties, extreme elongation, high reflectivity, anomalous acceleration, and lack of cometary activity had never been predicted by theoretical models of interstellar objects. This humbling experience reminded astronomers that nature often exceeds the boundaries of human imagination and theoretical frameworks. The Chase mission. In the aftermath of Oumuamua's discovery and the tantalizing mysteries it left in its wake, the international space community began seriously considering unprecedented missions to intercept and study interstellar objects. The most ambitious of these concepts was Project Lyra, a theoretical mission designed to catch up with Oumuamua and conduct detailed in situ analysis of humanity's first confirmed interstellar visitor. Project Lyra emerged from collaboration between researchers at the European Space Agency's Advanced Concepts team and scientists at institutions worldwide. The project's name, derived from the constellation Lyra, where Oumuamua's trajectory suggested it might have originated, captured both the poetic and scientific significance of attempting humanity's first interstellar chase mission. The technical challenges facing Project Lyra were staggering. By the time serious mission planning began in 2018, Oumuamua was already racing away from the Sun at speeds exceeding 26 kilometers per second. Catching up with an object moving at such velocities would require spacecraft technologies that push the boundaries of current capabilities, including advanced propulsion systems, sophisticated navigation algorithms, autonomous operation over interstellar distances. Initial trajectory analysis revealed that a conventional chemical rocket mission to Oumuamua was impossible with existing technology. The energy requirements for matching the object's velocity exceeded the capabilities of any launch vehicle ever built. Even using gravitational assists from multiple planets, a spacecraft would need to achieve velocity changes far beyond the reach of traditional propulsion systems. The Project Lyra team therefore focused on advanced propulsion concepts, including solar sails, using radiation pressure from sunlight for propulsion. Retry, AR, continue, ion drives. Electric propulsion systems powered by large solar arrays. Theoretical fusion rockets, advanced nuclear propulsion concepts. Solar electric propulsion emerged as the most promising near-term option, using efficient ion thrusters powered by large solar arrays to gradually accelerate a spacecraft over periods of years or decades. While such a mission would take an extremely long time to reach its target, the scientific payoff from direct analysis of interstellar material justified the extended timeline. Dr. Andreas Hein of the Initiative for Interstellar Studies led detailed feasibility studies that mapped out potential mission architectures for reaching Oumuamua. These studies revealed that even with the most optimistic assumptions about future propulsion technology, a mission launched in the early 2020s wouldn't reach the object until the late 2040s or early 2050s. By that time, Oumuamua would be so far from the sun that solar power would be marginal, requiring nuclear power sources for spacecraft operation. The scientific instruments for a Project Lyra mission would need to operate reliably for decades in the harsh environment of interstellar space. Advanced spectrometers, imaging systems, and sample collection devices would all need to function flawlessly after years of cosmic ray bombardment, extreme temperature cycling, and mechanical stress from constant acceleration. The mission would essentially require developing technology for true interstellar exploration decades ahead of schedule. Communication with a Project Lyra spacecraft would present its own set of challenges. By the time the mission reached Oumuamua, the spacecraft would be hundreds of times farther from Earth than any previous deep space mission. Radio signals would take hours to travel between Earth and the spacecraft, making real-time control impossible and requiring unprecedented levels of spacecraft autonomy. The 3I/Atlas opportunity. The discovery of 3I/Atlas in July 2025 has fundamentally changed the landscape for interstellar object missions. Unlike Oumuamua, which was discovered during its outbound journey, 3I/ATLAS was detected while still approaching the Sun. This advanced warning provides unprecedented opportunities for mission planning and potentially even rapid response missions using existing or near-future technology. Dr. Petra Konomos of NASA's Goddard Space Flight Center has led preliminary studies of potential missions to 3I/ATLAS, taking advantage of lessons learned from Project Lyra planning. The extended observation period before 3I/ATLAS reaches perihelion allows for detailed trajectory refinement, comprehensive mission planning, potentially even the construction and launch of purpose-built spacecraft. The trajectory of 3I/ATLAS, with its carefully orchestrated sequence of planetary flybys, presents unique opportunities for spacecraft missions. A probe launched to intercept the object during its Mars flyby could conduct detailed observations while the interstellar visitor is still relatively inactive. Alternatively, a mission designed to rendezvous with 3I/ATLAS during its Jupiter encounter could take advantage of the massive planet's gravitational field for trajectory adjustments and extended observation periods. The large size of 3I/ATLAS compared to Oumuamua also changes the mission requirements and opportunities. While the object's 7-mile diameter presents challenges for comprehensive mapping and analysis, it also provides a stable platform for extended observation and potentially even surface operations. A spacecraft equipped with landers or penetrators could conduct detailed subsurface analysis that would be impossible with smaller targets. Sample collection from 3I/ATLAS represents perhaps the greatest scientific opportunity in the history of space exploration. Direct analysis of pristine interstellar material could provide unprecedented insights into planetary formation processes in other star systems, the distribution of organic compounds throughout the galaxy, potentially even signs of past or present life from other worlds. The technological requirements for a 3I/ATLAS mission while still challenging, are significantly more achievable than those for Project Lyra. The object's approach trajectory allows for conventional launch windows and flight times measured in years rather than decades. Existing ion propulsion technology could potentially enable rendezvous missions, while advanced solar sails might allow for extended observation periods and sample return capabilities. International cooperation. International cooperation will be essential for any comprehensive 3/ATLAS mission. No single space agency possesses all the technologies and resources required for such an ambitious undertaking. The mission would likely require contributions from NASA, ESA, JAXA, and other agencies, along with potential involvement from private space companies with advanced capabilities. The timeline for a 3I/ATLAS mission depends heavily on the level of ambition and international commitment. A simple flyby mission using existing technology could potentially be launched within 2 to 3 years, arriving at the target during its outbound journey in the late 2020s. More sophisticated rendezvous and sample return missions would require longer development times, but could still reach the object while it remains within range of reasonable communication and navigation systems. The scientific instruments for a 3I/ATLAS mission would build upon decades of experience with comet and asteroid exploration. Advanced spectrometers capable of detecting trace compounds and unusual isotopic ratios would be essential for determining the object's true composition. High-resolution imaging systems could reveal surface features and structural details that might distinguish between natural and artificial origins. Perhaps most importantly, a 3I/ATLAS mission could include instruments specifically designed to search for signs of artificial construction or technology. Magnetometers could detect unusual magnetic fields that might indicate electronic systems. Radar sounders could map internal structure and identify hollow spaces or geometric patterns inconsistent with natural formation. Chemical analyzers could search for artificial compounds or materials not found in nature. The potential discoveries from a direct mission to 3I/ATLAS could fundamentally transform humanity's understanding of our place in the universe. Confirmation that the object represents natural interstellar material would provide unprecedented insights into planetary formation and evolution throughout the galaxy. Discovery of artificial components or technology would represent the most significant scientific discovery in human history. As mission planners around the world begin seriously considering 3I/ATLAS intercept scenarios, the lessons learned from Project Lyra provide valuable guidance for avoiding pitfalls and maximizing scientific return. The importance of international cooperation, technological development, flexible mission architectures all emerge as key factors for success. Whether or not a mission to 3I/ATLAS ultimately receives funding and approval, the planning process itself drives technological development and international cooperation that will benefit future space exploration efforts. The technologies developed for interstellar object missions will eventually enable true interstellar exploration, opening new frontiers for human expansion and discovery. The window of opportunity for 3I/ATLAS missions will eventually close as the object continues its journey into the outer solar system and beyond. The decisions made in the coming months and years will determine whether humanity seizes this unprecedented opportunity to directly study material from another star system, or watches helplessly as our third interstellar visitor fades into the cosmic distance, taking its secrets with it. The interstellar census. The discovery of 3 confirmed interstellar objects within less than a decade provides astronomers with an unprecedented opportunity to compare and contrast the characteristics of visitors from other star systems. Each object, Oumuamua 2I/Borisov, and now 3I/Atlas, exhibits distinct properties that collectively begin to define the range of phenomena we might expect from interstellar material, while also highlighting the unique characteristics that make each visitor scientifically valuable. 2I/Borisov discovered by amateur astronomer Gennady Borisov on August 30th, 2019, initially appeared to represent a more normal example of an interstellar object compared to the enigmatic Oumuamua. As Borisov approached the Sun, it developed a beautiful symmetrical coma and tail that exhibited all the characteristics astronomers expected from a pristine comet experiencing solar heating for the first time in millions or billions of years. The cometary activity of Borisov provided a stark contrast to Oumuamua's mysterious lack of outgassing. Spectroscopic observations revealed the presence of water vapor, carbon monoxide, and other typical cometary gases in abundances that match theoretical predictions for objects formed in the cold outer regions of planetary systems. The dust production and tail development followed patterns entirely consistent with natural cometary behavior, providing reassurance that interstellar objects could indeed behave as conventional astrophysical models predicted. However, detailed analysis of Borisov's composition revealed subtle but significant differences from solar system comets that hinted at its exotic origins. The carbon monoxide to water ratio in Borisov's coma was significantly higher than typical for comets from our Kuiper belt or Oort cloud, suggesting formation in a colder environment where carbon monoxide could remain stable in solid form. Isotopic measurements of the water vapor showed deuterium ratios unlike anything found in solar system materials. The nucleus of Borisov, estimated at roughly 1 kilometer in diameter, was significantly smaller than 3I/ATLAS, but much more conventional in size compared to typical comets. Its roughly spherical shape and moderate rotation, period of about 7.3 hours, suggested formation through standard accretion processes in the outer regions of its birth planetary system. Similarities and differences. In comparing Borisov with 3I/ATLAS, several striking similarities emerge that may define common characteristics of interstellar objects. Both exhibit compositions dominated by water ice and organic compounds. Both show evidence of formation in cold outer regions of planetary systems. Both possess isotopic signatures that clearly distinguish them from solar system materials. These commonalities suggest that large icy objects may be among the most common types of material ejected into interstellar space during planetary system evolution. The differences between Borisov and 3I/ATLAS are equally instructive. The dramatic size difference, 3I/ATLAS, contains roughly 1,000 times more material than Borisov, suggests different mechanisms of formation or ejection. While objects like Borisov might result from gravitational scattering of small comets during planetary migration, something as massive as 3I/ATLAS likely requires more dramatic events, stellar encounters, or the disruption of large planetary bodies. The cometary activity patterns also differ significantly between the two objects. Borisov began showing detectable coma development at approximately 6 astronomical units from the Sun, typical for water, ice-dominated comets. 3I/ATLAS, despite its much larger size and presumably greater volatile inventory, has shown no clear signs of cometary activity as of late August 2025, even at distances where substantial outgassing might be expected. Oumuamua represents the most extreme example of unusual behavior among our interstellar visitors. Its lack of detectable cometary activity, combined with mysterious non-gravitational acceleration, sets it apart from both Borisov and 3I/ATLAS. The object's extreme elongation, high reflectivity, and small size create a unique profile that remains difficult to explain through conventional models of natural object formation. Comparing all three objects reveals interesting patterns in their discovery circumstances and observational opportunities. Oumuamua was discovered during its outbound journey, providing only a brief window for detailed study before it faded beyond detection limits. Borisov was detected during its approach, allowing for extensive observation campaigns, but still providing only a limited time window. 3I/ATLAS, discovered during its inbound journey, offers the longest observational baseline and the greatest opportunity for comprehensive study. The size spectrum. The trajectories of the three objects also show interesting contrasts. Oumuamua's path through the inner solar system was relatively straightforward, with no particularly close planetary encounters. Borisov's trajectory brought it closer to the Sun than 3I/ATLAS will approach, but without the precisely choreographed sequence of planetary flybys that characterizes the current visitor's path. Size-wise, the three objects span an enormous range that may reflect the diversity of interstellar material. Oumuamua, at roughly 400 meters in length, represents the smallest class of detectable interstellar objects. Borisov, at approximately 1 kilometer in diameter, falls into the size range of typical comets from our outer solar system. 3I/ATLAS, at 7 miles in diameter, represents a new class of truly massive interstellar objects that may be rare but scientifically invaluable when detected. The compositional analysis of all three objects provides insights into the chemical diversity of interstellar material. Oumuamua's composition remains largely unknown due to its lack of outgassing and brief observation window. Borisov showed clear evidence of water ice, carbon monoxide, and organic compounds with unusual isotopic ratios. 3I/ATLAS appears to contain pristine water ice and complex organic materials preserved over potentially billions of years. These compositional differences may reflect formation in different types of stellar systems or at different epochs in galactic history. Oumuamua's unusual properties might indicate formation under extreme conditions or in an environment unlike typical planetary systems. Borisov's composition suggests formation in a cold, carbon-rich environment around a star with different metallicity than our Sun. 3I/ATLAS appears to preserve materials from a stellar system with higher heavy element abundance and older age. Detection evolution. The thermal properties of the three objects also vary significantly. Oumuamua showed unusual thermal characteristics that contributed to debates about its composition and structure. Borisov exhibited thermal behavior entirely consistent with natural cometary material. 3I/ATLAS remains largely untested thermally, as it has not yet approached close enough to the Sun for significant heating. The detection methods for all three objects have improved dramatically with each discovery. Oumuamua was initially mistaken for an asteroid and only recognized as interstellar after several nights of observations. Borisov was immediately suspected of interstellar origin due to its unusual trajectory, and confirmation came quickly. 3I/ATLAS was identified as potentially interstellar within days of discovery, reflecting improvements in automated detection and analysis systems. The scientific return from studying each object has varied considerably. Oumuamua generated enormous scientific interest and debate, but provided limited definitive answers about its nature or origins. Borisov offered clear insights into interstellar cometary composition and behavior, while raising new questions about the diversity of planetary formation processes. 3I/ATLAS promises to provide the most comprehensive data set yet available for any interstellar object. Looking forward, the comparison between these three visitors provides valuable guidance for interpreting future interstellar object discoveries. The range of sizes, compositions, and behaviors observed suggests that interstellar space contains a diverse population of objects with varying origins and characteristics. Some, like Borisov, may represent relatively straightforward examples of natural cometary material. Others, like Oumuamua and possibly 3I/ATLAS, may challenge conventional understanding and require new theoretical frameworks. The progression from Oumuamua through Borisov to 3I/ATLAS also demonstrates the rapid advancement in our ability to study interstellar objects. Each successive visitor has been observed with more sophisticated instruments, better theoretical understanding, and more comprehensive observational campaigns. This technological and methodological progress ensures that future interstellar visitors will be studied with unprecedented detail and precision. The cosmic silence. The dark forest theory, popularized by Chinese science fiction author Liu Cixin in his acclaimed three-body problem trilogy, presents one of the most chilling possible explanations for the apparent silence of the universe. Also known as the dark forest hypothesis, this concept addresses the famous Fermi paradox, the puzzling contradiction between the high probability of extraterrestrial civilizations and the complete lack of evidence for their existence. The theory takes its name from a haunting metaphor presented in Liu's work. The universe is like a dark forest, where every civilization is a hunter, moving silently through the trees. The moment any hunter reveals their location by making noise, they risk being discovered and eliminated by other hunters who view them as potential threats. In this cosmic forest, silence equals survival, while detection means death. The underlying logic of the dark forest theory rests on several key assumptions about the nature of civilizations and their interactions. First, it assumes that survival is the primary goal of any civilization. Second, it posits that civilizations cannot be certain of the intentions of other civilizations they encounter. Third, it suggests that technological advancement inevitably leads to the capability for interstellar destruction. Finally, it argues that the distances and communication delays inherent in interstellar space make peaceful first contact virtually impossible. Under these assumptions, any civilization that detects another faces an impossible choice. They cannot determine whether the discovered civilization is peaceful or hostile. They cannot effectively communicate due to the vast distances and time delays involved in interstellar messaging. They cannot assume that even a currently peaceful civilization will remain peaceful as it continues to evolve technologically. The logical response, therefore, is immediate preemptive strike, what the theory terms a dark forest strike. The hiding game. This creates a cosmic Mexican standoff where every civilization remains silent and hidden, knowing that detection by another civilization likely means annihilation. Advanced civilizations develop increasingly sophisticated camouflage and stealth technologies while maintaining constant vigilance for signs of others. The galaxy becomes populated by hidden watchers, each afraid to reveal themselves, but desperately trying to detect others before being detected themselves. The implications of the dark forest theory extend far beyond simple hide-and-seek between civilizations. It suggests that advanced civilizations would develop extensive passive surveillance networks, using sophisticated probes and monitoring stations to gather intelligence about potential threats while maintaining their own concealment. These reconnaissance systems would need to appear completely natural to avoid detection, masquerading as asteroids, comets, or other innocuous space debris. In the context of 3I/ATLAS, the dark forest theory provides a framework for interpreting the object's unusual characteristics and trajectory. If the theory is correct, then what we interpret as an interstellar comet might actually be a sophisticated surveillance probe designed to study our solar system while maintaining perfect camouflage as a natural object. The size of 3I/ATLAS becomes particularly significant under this interpretation. A 7-mile wide object provides ample space for concealing advanced instrumentation, power systems, and data processing capabilities while maintaining the external appearance of a natural comet. The object's large mass would provide excellent shielding against cosmic radiation and solar heating, protecting sensitive electronics during the long journey between star systems. The trajectory of 3I/ATLAS also aligns remarkably well with what a dark forest reconnaissance mission might attempt to accomplish. The carefully orchestrated sequence of planetary flybys maximizes observational opportunities while minimizing the risk of detection through unusual behavior. The timing of perihelion on the far side of the Sun from Earth creates a natural period of concealment during which any artificial systems could operate without risk of observation from our most sensitive instruments. Perfect camouflage. The pristine composition detected in 3I/ATLAS could represent either genuine ancient materials preserved from another star system or sophisticated mimicry designed to fool spectroscopic analysis. Advanced alien technology might easily be capable of creating artificial ice and organic compounds with isotopic signatures that perfectly mimic materials from distant stellar systems. Under the dark forest scenario, the purpose of 3I/ATLAS would be comprehensive intelligence gathering about our solar system and its potential inhabitants. The probe would be designed to assess our technological capabilities, monitor our communications, analyze our planetary environments, determine whether humanity represents a current or future threat to its creators. The probe might carry sophisticated passive sensors capable of detecting electromagnetic emissions from Earth, analyzing our atmospheric composition for signs of industrial activity, and monitoring our space-based assets for evidence of advanced technology. It might even carry active scanning systems that operate only during periods when they're shielded from Earth-based observation, such as during the perihelion passage behind the Sun. The dark forest theory also provides an explanation for why such a probe would eventually leave our solar system rather than remaining for long-term observation. Extended presence would increase the risk of detection and potentially reveal the probe's artificial nature through subtle behavioral anomalies. A single flyby mission, however, could gather comprehensive intelligence while maintaining perfect camouflage as a natural interstellar object. Critics of applying the dark forest theory to real astronomical observations point out several significant problems with this interpretation. The theory assumes that all civilizations develop along similar technological and sociological paths, which may not reflect the true diversity of possible evolutionary outcomes. It also assumes that interstellar destruction is both feasible and preferable to other forms of interaction, which remains speculative given our limited understanding of advanced technology. Furthermore, the theory relies heavily on game theory assumptions that may not apply to alien psychology or decision-making processes. Human concepts of threat assessment, risk management, and strategic thinking might be completely irrelevant to genuinely alien intelligences that evolved under different environmental and evolutionary pressures. The paradox of fear. The dark forest theory also struggles to explain why a civilization advanced enough to construct interstellar reconnaissance probes would be concerned about a species as technologically primitive as current humanity. Any civilization capable of interstellar travel presumably possesses technological advantages so overwhelming that early-stage civilizations like ours would pose no meaningful threat for thousands or millions of years. Despite these criticisms, the dark forest theory remains compelling because it provides a coherent explanation for both the Fermi paradox and the unusual characteristics of objects like 3I/ATLAS. It suggests that the universe might be teeming with intelligent life, but that this life remains hidden behind veils of technological sophistication that make it virtually undetectable to less advanced civilizations. Whether or not the dark forest theory accurately describes the true state of galactic civilization, it serves as a valuable framework for evaluating anomalous observations like 3I/ATLAS. By considering the possibility that interstellar objects might not always be what they appear to be, we open ourselves to detecting signs of intelligence that might otherwise be dismissed as natural phenomena. The theory also highlights the potential risks associated with our own growing technological capabilities and increasingly visible presence in the galaxy. If the dark forest theory is correct, humanity's radio emissions, space exploration activities, and other signs of technological development might already have attracted unwanted attention from hidden observers throughout our local galactic neighborhood. The question then becomes, if advanced civilizations really do hide in the cosmic dark, sending disguised probes to study younger species, how would we recognize such reconnaissance systems? What signatures would betray their artificial nature? What behavioral patterns would distinguish sophisticated mimicry from genuine natural phenomena? These are not idle philosophical questions. They represent practical challenges for astronomers studying objects like 3I/ATLAS. The line between extreme caution and willful blindness is thin, and crossing it in either direction carries consequences. Dismiss every anomaly as natural, and we might overlook humanity's first contact with extraterrestrial intelligence. See artificial design in every statistical improbability, and we descend into pattern-seeking delusion. The truth, as always, lies somewhere in the careful accumulation of evidence. Paradigm shift. The 3I/ATLAS phenomenon has forced the SETI community to confront the fundamental assumptions about how extraterrestrial intelligence might manifest in our cosmic neighborhood. For over 6 decades, SETI research has predominantly focused on detecting radio signals, optical pulses, and other obvious artificial transmissions from distant civilizations. The possibility that alien intelligence might visit our solar system in the form of sophisticated reconnaissance probes represents a paradigm shift that could reshape the entire field. Dr. Jill Tarter, former director of the SETI Institute and a pioneer in the search for extraterrestrial intelligence, acknowledges that 3I/ATLAS has opened our eyes to detection modalities we hadn't seriously considered. Traditional SETI approaches assume that advanced civilizations would want to announce their presence through detectable signals. However, a reconnaissance mission would likely prioritize stealth and discretion over communication, requiring entirely different detection strategies. The implications for SETI methodology are profound. If interstellar visitors like 3I/ATLAS represent a genuine phenomenon, then future search efforts must expand beyond electromagnetic signals to include systematic monitoring of unusual objects within our solar system. This shift requires new observational capabilities, analysis techniques, theoretical frameworks for distinguishing between natural and artificial phenomena. The most immediate impact concerns the need for enhanced interstellar object detection and tracking systems. Current astronomical surveys like the Catalina Sky Survey and Linear were designed primarily to identify potentially hazardous asteroids rather than interstellar visitors. While these systems successfully detected both Oumuamua and 3I/ATLAS, they lack the sensitivity and coverage necessary for comprehensive monitoring of interstellar traffic. Dr. Robert Warwick of the Institute for Astronomy at the University of Hawaii, who led the team that discovered Oumuamua, advocates for dedicated interstellar object survey programs. These specialized systems would employ wide-field telescopes with advanced image processing algorithms specifically designed to identify objects with hyperbolic trajectories and unusual characteristics. The goal would be early detection of interstellar visitors while they're still in the outer solar system, allowing for extended observation periods and potential spacecraft intercept missions. The Vera Rubin era. The Vera C. Rubin Observatory, which began operations in 2024, represents a significant step toward comprehensive sky monitoring. Its Large Synoptic Survey telescope will photograph the entire visible sky every few nights, creating an unprecedented database of astronomical observations. This systematic approach should dramatically improve our ability to detect and characterize interstellar objects, potentially revealing whether visitors like 3I/ATLAS are rare anomalies or representatives of regular interstellar traffic. However, enhanced detection capabilities raise complex questions about data interpretation and scientific standards. The SETI community has long grappled with the balance between open scientific inquiry and responsible speculation. Claims of potential extraterrestrial contact carry enormous implications for humanity and require extraordinary evidence to support extraordinary conclusions. The 3I/ATLAS case illustrates this challenge perfectly. While statistical analysis suggests improbable trajectory characteristics, the evidence remains circumstantial and subject to alternative explanations. Publishing speculative interpretations risks undermining SETI's scientific credibility, while excessive caution might cause researchers to overlook genuine evidence of extraterrestrial visitation. Dr. Seth Shostak of the SETI Institute argues for transparent reporting of unusual observations while maintaining rigorous analytical standards. The scientific method depends on open discussion of data and interpretations, he explains. Our responsibility is to present evidence objectively, while clearly distinguishing between observations and speculations about their implications. This approach requires new protocols for investigating potentially artificial objects. The SETI community has developed extensive guidelines for verifying and reporting electromagnetic signals, including requirements for independent confirmation and peer review before public announcement. Similar standards must be established for physical objects that might represent extraterrestrial technology. New protocols. The International Astronomical Union has begun developing frameworks for interstellar object classification and investigation procedures. These protocols emphasize systematic observation, statistical analysis, collaborative research approaches that minimize the influence of individual bias or wishful thinking. The goal is establishing objective criteria for distinguishing between natural phenomena and genuinely anomalous objects that might warrant extraordinary claims. Beyond detection and analysis challenges, 3I/ATLAS raises profound questions about human preparedness for potential contact with extraterrestrial intelligence. If reconnaissance probes are indeed visiting our solar system, they represent a form of contact that differs dramatically from the distant radio signals that SETI has long anticipated. The psychological and sociological implications of nearby alien surveillance could prove far more challenging than receiving messages from distant civilizations. Radio signals from thousands of light years away pose no immediate threat and allow humanity time to process the implications of contact. Physical objects within our solar system suggest active interest in human civilization and raise immediate questions about alien intentions and capabilities. Dr. Douglas Vakoch, president of METI International, emphasizes the need for serious consideration of contact scenarios involving visiting spacecraft. We've spent decades preparing for the possibility of receiving radio messages from distant stars, he notes. We're far less prepared for the possibility that advanced civilizations might be studying us directly through reconnaissance missions. This preparedness gap extends to governmental and institutional responses. While protocols exist for handling potential SETI detections, they assume contact through electromagnetic signals rather than physical visitation. The 3I/ATLAS phenomenon highlights the need for comprehensive frameworks addressing all possible manifestations of extraterrestrial intelligence, including scenarios that might require immediate rather than contemplative responses. The detection paradox. The implications for space exploration policy are equally significant. If interstellar visitors are indeed present in our solar system, future space missions might encounter artificial objects or evidence of extraterrestrial activity. Space agencies must consider these possibilities when designing exploration programs and developing contingency protocols for unexpected discoveries. NASA's Planetary Defense Coordination Office, established to track potentially hazardous asteroids, has begun incorporating interstellar object monitoring into its mission scope. This expansion reflects growing recognition that unusual visitors like 3I/ATLAS warrant careful tracking regardless of their ultimate origin. The office's dual focus on natural hazards and potentially artificial objects represents an important evolution in space surveillance priorities. The confirmation of artificial origin for an object like 3I/ATLAS would represent the most significant discovery in human history, fundamentally altering our understanding of our place in the universe. Such confirmation would prove that advanced civilizations exist. They possess interstellar travel capabilities. They consider our solar system worthy of investigation. The implications would extend far beyond astronomy to encompass philosophy, religion, politics, and every aspect of human culture. However, the threshold for such confirmation must remain extraordinarily high. The history of science includes numerous examples of initially promising anomalies that ultimately received conventional explanations. The canals of Mars, pulsars initially dubbed little green men, and various purported biosignatures have all demonstrated the danger of premature conclusions about extraterrestrial phenomena. As summer transitions into autumn, 3I/ATLAS continues its inexorable approach toward the sun, and the astronomical community enters the most critical observation period since the object's discovery. The next 6 months will likely determine whether this 7-mile-wide visitor represents a natural relic from a distant star system or something far more extraordinary. September 2025 marks the beginning of the crucial test for 3I/ATLAS's nature. By early September, the object will have crossed the 2 astronomical unit threshold, the distance at which most comets begin showing clear signs of activity. Water ice sublimation should become readily detectable. Cyanogen and diatomic carbon emissions should appear in spectroscopic observations. A visible coma should start forming around the nucleus. If these signatures fail to appear, the anomaly will become impossible to ignore. Professional observatories worldwide have coordinated an unprecedented observation campaign for September. The European Southern Observatory's Very Large Telescope has allocated nightly observation slots throughout the month. The Keck Observatory in Hawaii will conduct continuous spectroscopic monitoring. The Gemini telescopes, both north and south, will contribute high-resolution imaging and spectroscopy. Space-based assets are equally committed. The Hubble Space Telescope will perform weekly ultraviolet spectroscopy observations, specifically designed to detect even trace amounts of cometary gases. The James Webb Space Telescope has scheduled multiple infrared imaging and spectroscopy sessions that could reveal subtle thermal signatures invisible to ground-based instruments. Amateur astronomers around the world will also play a crucial role. By mid-September, 3I/ATLAS should brighten to approximately magnitude 16, still too faint for visual observation, but accessible to amateur telescopes equipped with sensitive CCD cameras. A global network of amateur observers will provide continuous monitoring that complements professional observations, potentially catching transient events that might be missed by scheduled telescope time. The search for cometary activity goes beyond simple detection of gases. Astronomers will also look for dust production, particles released from the nucleus that could form a visible coma or tail, jets or outbursts, localized regions of enhanced activity that might indicate surface features or structural weaknesses, brightness changes, variations in reflected sunlight that might indicate surface alterations due to sublimation. Polarization and signatures, changes in the polarization of reflected light that could reveal dust, particle characteristics. October 2025 represents the climax of 3I/ATLAS's journey through our solar system. The month contains the object's 2 most significant milestones, the Mars flyby on October 3rd and perihelion passage on October 29th. October 3rd, the Mars encounter. As 3I/ATLAS passes within 18 million miles of Mars, spacecraft in Martian orbit will have their best opportunity to observe an interstellar object at relatively close range. NASA's MAVEN spacecraft will deploy its full suite of atmospheric instruments to search for any gases emanating from 3I/ATLAS. The Imaging Ultraviolet Spectrograph, IUVS, will scan for UV emissions from cometary molecules. The Neutral Gas and Ion Mass Spectrometer, NGIMS, will attempt to detect any neutral atoms or ions in the object's vicinity. The European Space Agency's Mars Express will contribute its high-resolution stereo camera, HRSC, for detailed imaging. If 3I/ATLAS maintains its estimated 7-mile diameter, the spacecraft should be able to resolve the object as more than a point of light, potentially revealing surface features, rotation characteristics, and any evidence of coma development. China's Tianwen-1 orbiter will provide additional observational perspectives, particularly valuable given its different orbital geometry around Mars. On the Martian surface, the Perseverance and Curiosity rovers may attempt imaging if atmospheric conditions permit, and the object appears above the horizon during suitable observation windows. While the rover's cameras aren't optimized for astronomical observations, their unique surface perspective could provide valuable data about 3I/ATLAS's appearance and any coma development. October 29th, perihelion. The perihelion passage represents the moment of truth for all theories about 3 3I/ATLAS. At its closest approach to the Sun, 1.36 astronomical units, the object will experience heating intense enough to sublimate virtually any volatile materials present in its composition. Surface temperatures will reach approximately 150 to 200 Kelvin, negative 123 to negative 73 degrees Celsius, well above the sublimation point for many ices. If 3I/ATLAS is a natural comet, this is when dramatic activity must occur. The solar heating should trigger widespread sublimation across the nucleus surface. Water vapor production should increase by orders of magnitude. The coma should expand to millions of kilometers. A tail, perhaps multiple tails, one of dust and one of ionized gas, should stream millions of miles behind the object. Unfortunately, perihelion occurs when 3I/ATLAS is on the far side of the Sun from Earth, hidden by solar glare and impossible to observe with most ground-based telescopes. This timing creates both frustration and intrigue for the scientific community. The primary observers during perihelion will be spacecraft positioned at the Sun-Earth L, 1 Lagrange point, approximately 1 million miles sunward of Earth. The Solar and Heliospheric Observatory, SOHO, will monitor 3I/ATLAS using its LASCO coronagraphs, which block the Sun's bright disk while revealing fainter objects in the surrounding corona. These instruments have observed thousands of comets passing close to the Sun and will provide crucial data about any cometary activity during 3I/ATLAS's perihelion passage. The Solar Dynamics Observatory will contribute additional observations using its extreme ultraviolet imaging capabilities. While primarily designed to study the Sun itself, SDO's instruments can detect bright cometary emissions if they occur. Meanwhile, Mars-based observers will maintain their advantageous position. The red planet's orbital geometry places it roughly perpendicular to the Earth Sun 3Y/ATLAS alignment during perihelion, meaning spacecraft at Mars can observe 3I/ATLAS during its period of maximum solar heating without interference from solar glare. This is precisely the kind of observational choreography that feeds speculation about intentional design, optimal viewing opportunities distributed across multiple platforms, as if the trajectory were planned to maximize scientific data collection while minimizing Earth-based observation during critical moments. November 2025 brings 3I/ATLAS back into view for Earth-based observers as it emerges from behind the Sun. By early November, the object will be positioned for observation from Northern Hemisphere telescopes. More importantly, it will have passed through perihelion, and any changes to its appearance or behavior caused by intense solar heating will be clearly visible. This post-perihelion observation period is critical for several reasons. If 3I/ATLAS developed cometary activity during perihelion, that activity should persist for weeks or months afterward, as the nucleus continues outgassing while cooling. The coma might even expand and brighten as it moves away from the Sun, as sublimated gases have more time to disperse into space. Conversely, if no cometary activity appeared during perihelion, the continued absence of signatures in November will constitute definitive evidence that 3I/ATLAS behaves unlike any natural comet previously observed. The James Webb Space Telescope will play a starring role in November observations. JWST's unprecedented infrared sensitivity allows it to detect even trace amounts of water vapor, carbon dioxide, methane, and other volatiles. Its spectroscopic capabilities can analyze isotopic ratios in any detected gases with precision impossible from ground-based telescopes. If artificial systems aboard 3I/ATLAS operated during the perihelion passage, perhaps using the Sun's energy to power instruments or communications, the aftermath might reveal telltale signatures, unexpected heat distribution patterns, geometric structures in any coma that developed or controlled outgassing patterns inconsistent with natural sublimation. December 19th, Earth's closest approach. On December 19, 2025, 3I/ATLAS will pass approximately 170 million miles from Earth, its closest approach to our planet during its entire journey through the solar system. This distance places the object at roughly the same range as Mars at opposition, making it accessible to Earth's most powerful telescopes while ensuring no gravitational interaction with our planet. The December observation window represents the first extended opportunity for detailed Earth-based study of 3I/ATLAS after perihelion. Any changes in appearance, composition, or behavior caused by solar heating will be clearly visible and quantifiable. Ground-based observatories will conduct intensive photometric monitoring, measuring how the object's brightness varies over time. These observations can reveal rotation rate changes that might indicate mass loss or structural modifications, color variations that could suggest compositional differences across the surface, light curve anomalies that might betray artificial structures or controlled activities. Radio telescopes will also intensify their search for electromagnetic emissions. The Very Large Array in New Mexico, the Arecibo Observatory's successor facilities, and radio telescopes worldwide will conduct sensitive searches for any signals emanating from 3I/ATLAS. The object's distance will be optimal for radio observations, close enough for strong signal detection, but far enough to avoid interference from solar radio emissions. If 3I/ATLAS is artificial, December might represent an optimal time for communication or data transmission back to its creators. The object will have completed its close-range survey of the inner solar system, collected comprehensive data, and positioned itself for efficient transmission across interstellar distances. Early 2026 marks the final act of 3I/ATLAS's grand tour. By January, the object will be moving steadily outward from the Sun, crossing Earth's orbit and heading toward the outer solar system. Brightness will gradually decrease as distance increases, but major telescopes will maintain observation campaigns through the crucial Jupiter encounter in March. March 16, 2026. The Jupiter Passage. The final major milestone occurs when 3I/ATLAS passes just 33 million miles above Jupiter's cloud tops, well within the giant planet's powerful magnetosphere. This encounter provides the last major opportunity for close-range observation and potentially the most revealing test of 3I/ATLAS's true nature. NASA's Juno spacecraft, currently in polar orbit around Jupiter, will be uniquely positioned to study 3I/ATLAS during the encounter. Juno's instruments, designed to probe Jupiter's interior and magnetosphere, will be capable of detecting any interactions between the interstellar object and Jupiter's intense magnetic field and radiation belts. The JunoCam imaging instrument will capture high-resolution photographs of 3I/ATLAS from distances potentially as close as 30 million miles, far closer than any Earth-based telescope can achieve. These images should resolve surface features and structural details invisible from Earth. The Jovian Infrared Auroral Mapper, JIRAM, will provide infrared spectroscopy that could detect subtle thermal signatures indicative of active systems or unusual compositions. Most intriguingly, Juno's Stellar Reference Unit, SRU, a star tracker camera typically used for spacecraft navigation, will be capable of detecting faint dust particles shed by 3I/ATLAS. Jupiter's magnetic field can trap charged particles, and any dust released from the interstellar object might be captured in the magnetosphere, where Juno could sample it directly. This would represent the first direct physical sampling of interstellar material in human history. The gravitational interaction between 3I/ATLAS and Jupiter will also provide scientists with their final opportunity to precisely measure the object's mass. By tracking exactly how Jupiter's gravity deflects the object's trajectory, astronomers can calculate its mass with unprecedented accuracy, resolving any remaining uncertainties about its density and internal structure. The Jupiter encounter is particularly significant for evaluating artificial origin hypotheses. If 3I/ATLAS contains electronic systems or artificial materials, the intense radiation environment within Jupiter's magnetosphere would subject those systems to extreme stress. Natural materials would respond to this radiation in predictable ways, producing characteristic emissions or exhibiting specific types of damage detectable by Juno's instruments. Artificial systems, however sophisticated, would need extraordinary shielding to survive Jupiter's radiation belts. Any anomalous responses to the radiation environment, unexpected electromagnetic emissions, unusual thermal signatures, or geometric patterns in any material shed into the magnetosphere could provide evidence of artificial construction. After the Jupiter encounter, 3I/ATLAS will begin its final departure from our solar system. The object will continue on its hyperbolic trajectory, gradually fading from view as it moves beyond the reach of even our most powerful telescopes. By mid-2026, only the largest observatories will be able to track it. By late 2026 or early 2027, it will fade beyond detection limits entirely, becoming one more anonymous wanderer in the cosmic dark between the stars. As 3I/ATLAS continues its journey, the accumulated observations and debates raise profound questions about the nature of scientific proof and the standards of evidence required for extraordinary claims. How do we distinguish between a genuinely artificial object and a natural phenomenon that merely appears designed? What level of evidence would constitute definitive proof of extraterrestrial visitation? And perhaps most uncomfortably, could we even recognize alien technology if it were deliberately designed to appear natural? These are not merely academic questions. They strike at the heart of how we understand reality and evaluate evidence. The history of science is filled with examples of phenomena that initially seemed mysterious or even supernatural, but ultimately received natural explanations. Ball lightning, aurora borealis, meteor showers, and countless other phenomena once attributed to divine intervention or supernatural causes are now understood through physics and chemistry. This historical pattern suggests caution when evaluating unusual observations. The principle of parsimony, often called Occam's razor, suggests that we should prefer the simplest explanation consistent with available evidence. Natural processes, while sometimes requiring unusual circumstances, generally represent simpler explanations than hypotheses invoking advanced alien civilizations with unknowable motivations and capabilities. However, parsimony can also become a straitjacket that prevents recognition of genuinely extraordinary phenomena. Dr. Michael Shermer, founding publisher of Skeptic magazine, notes that the principle of parsimony is a guideline, not a law. Sometimes the simplest explanation really is something we've never seen before happened. The challenge lies in distinguishing between healthy scientific skepticism and dogmatic resistance to new ideas. In the case of 3I/ATLAS, we face multiple layers of uncertainty. First, the observational uncertainty. Do we have accurate measurements of the object's trajectory, composition, and behavior? Second, the interpretive uncertainty. Are we correctly understanding what those measurements mean? Third, the theoretical uncertainty. Do our models of natural phenomena adequately account for all possible natural explanations? Fourth, the philosophical uncertainty. What standards of evidence should we require for claims about artificial origin? Each layer introduces opportunities for both error and bias. Perhaps the most vexing aspect of the 3I/ATLAS debate concerns what philosophers of science call the technology recognition problem. How would we recognize technology created by a civilization potentially millions or billions of years more advanced than our own? Human technology follows certain recognizable patterns: geometric regularity, artificial materials, electromagnetic emissions, thermal signatures. We build things from metals and plastics, power them with electricity or combustion, and design them with straight lines and precise angles because these approaches work for our level of technological development. But what about a civilization a million years ahead of us? Would their technology even be recognizable as technology? Might they employ materials and energy sources we don't understand, operating on principles we haven't discovered? Could they create objects that are simultaneously artificial and biological, engineered yet alive in ways we can't conceptualize? Science fiction author Arthur C. Clarke famously observed that any sufficiently advanced technology is indistinguishable from magic. We might extend this principle. Any sufficiently advanced technology might be indistinguishable from nature itself. This creates a profound epistemological problem. If we establish looking natural as evidence against artificial origin, we might systematically overlook artificial objects specifically designed to appear natural. But if we allow that artificial objects might perfectly mimic natural ones, we lose any reliable method for distinguishing between the two. Dr. Stephen Dick, former NASA chief historian and author of The Biological Universe, argues that we need to fundamentally rethink our assumptions about what constitutes evidence of intelligence. We've been looking for intelligence that thinks like us, builds like us, communicates like us, Dick notes, but intelligence that evolved under completely different conditions might express itself in ways we wouldn't recognize. The question isn't, does this look like our technology? But does this exhibit patterns inconsistent with known natural processes? This reframing shifts the burden of proof. Instead of looking for positive evidence of artificial construction, metal, circuitry, radio signals, we might look for negative evidence, the absence of expected natural phenomena, statistical improbabilities beyond reasonable thresholds, or behaviors that violate established physical principles. 3. I/ATLAS exhibits several such anomalies. Missing cometary signatures, despite composition and distance suggesting they should appear. Trajectory, with 1 in 20,000 probability of occurring by chance. Size far exceeding any previously detected interstellar object. Pristine preservation over potentially billions of years. Perfect choreography of planetary encounters. Individually, each anomaly might be explained through unusual but natural circumstances. Collectively, they create a pattern that challenges conventional interpretation. If 3I/ATLAS does represent artificial technology, what would that mean for humanity? The implications extend far beyond confirming that we're not alone in the universe. They touch on fundamental questions about our cosmic significance, our technological future, and potentially our survival as a species. The intelligence question. Confirmation of artificial origin would prove that intelligence can arise elsewhere in the universe. It can survive long enough to develop interstellar travel. It considers our solar system worthy of investigation. Advanced civilizations may be far more common than the Fermi paradox suggests. The motivation. Question: why would an advanced civilization send reconnaissance probes to our solar system? Possible motivations include scientific curiosity, the same drive that motivates human space exploration; threat assessment, determining if humanity might pose future dangers; resource evaluation, cataloging potentially valuable materials or locations; biological interest, studying life and ecosystems throughout the galaxy; historical documentation, recording the development of younger civilizations. None of these motivations necessarily implies hostility, but none guarantees benevolence either. The temporal question: when was 3I/ATLAS launched? If the object traveled through interstellar space for millions of years, it might have been launched when Earth was still home, only to simple microbial life. Its creators might not even know that intelligent life currently exists on our planet. Alternatively, if it was launched more recently and traveled at high speed, it might represent a targeted mission specifically designed to study an already detected technological civilization. The communication question: if 3I/ATLAS is artificial, will it attempt to communicate? The absence of obvious signals doesn't mean communication isn't occurring. An advanced civilization might use communication methods we can't detect. Quantum entanglement, gravitational waves, modulated neutrinos, or phenomena we haven't discovered. Alternatively, the probe might be entirely passive, designed solely to observe and record, transmitting its findings back to its creators via methods invisible to us, the fleet. Question: is 3I/ATLAS unique or one of many? If advanced civilizations routinely send reconnaissance probes to survey nearby star systems, our solar system might host multiple such objects at any given time. Most might remain in the outer solar system, quietly observing from distances that make detection nearly impossible. The 3 interstellar objects we've detected, Oumuamua, Borisov, and 3I/ATLAS, might represent only the tiny fraction of interstellar traffic that happens to pass close enough to Earth for detection. The response question: how should humanity respond if artificial origin is confirmed? This question has no easy answer and likely depends on the level of certainty achieved. Strong but not definitive evidence might warrant increased vigilance and continued monitoring. Definitive proof would require careful consideration of potential communication attempts, with input from international bodies, scientific communities, and potentially humanity as a whole. The discovery would also raise urgent questions about our own behavior. If we're being observed, what message does our activity send? Our radio and television broadcasts have been propagating into space for decades. Our nuclear detonations created unmistakable signatures of technological civilization. Our atmospheric composition reflects industrial chemistry, unlike anything natural. We may already be visible to anyone watching carefully. The numbers game. As we approach the conclusion of our journey through the mystery of 3I/ATLAS, it's worth stepping back to consider the broader statistical context. The discovery of 3 interstellar objects within 8 years suggests that such visitors are far more common than previously believed. Before Oumuamua, most astronomers expected that interstellar objects passing through our solar system would be extremely rare, perhaps one every few decades or centuries. The rapid succession of 3 confirmed detections suggests either remarkable luck or, more likely, that interstellar space is populated by vastly more wanderers than theoretical models predicted. Extrapolating from current detection rates, astronomers estimate that at any given moment, there might be several interstellar objects within our solar system, most too small, too dark, or too distant to detect with current technology. The Vera Rubin Observatory, with its unprecedented sky survey capabilities, may reveal dozens or even hundreds of interstellar visitors over the coming decade. This growing census will help answer crucial questions about the frequency, size distribution, and characteristics of interstellar objects. But statistics cut both ways in the 3I/ATLAS debate. On one hand, if interstellar objects are common, the detection of one with an unusual trajectory becomes less surprising. Random chance operating over many samples eventually produces unlikely outcomes. On the other hand, if interstellar visitors are frequent, the probability that at least some represent artificial reconnaissance increases. The galaxy contains hundreds of billions of star systems and has existed for over 13 billion years. Even if only a tiny fraction of stars host technological civilizations, and even if only a tiny fraction of those civilizations send out probes, the cumulative number of artificial objects wandering through the galaxy could be substantial. The Drake equation, proposed by astronomer Frank Drake in 1961, attempts to estimate the number of active, communicative extraterrestrial civilizations in our galaxy. While the equation's variables remain highly uncertain, most reasonable estimates suggest that if intelligent life can arise at all, it should be relatively common. The apparent absence of detected civilizations, the Fermi paradox, therefore requires explanation. The dark forest hypothesis provides one explanation. Civilizations hide because detection means death. An alternative explanation suggests that advanced civilizations transcend physical exploration entirely, moving into virtual realities or higher dimensions we can't perceive. Another possibility: we're simply early. Perhaps intelligence is rare enough that most civilizations are still too primitive for interstellar travel, and we're among the first technological species to reach for the stars. Or perhaps, most troubling of all, advanced civilizations are common but short-lived. Perhaps the transition to technological maturity presents existential risks that most species fail to navigate. Climate catastrophe, nuclear annihilation, artificial intelligence gone wrong, or other dangers we haven't imagined might destroy most civilizations before they achieve interstellar travel. In this scenario, the galaxy might be littered with dead worlds and ancient probes sent by civilizations that no longer exist. The silence of the sphere. There's a particular loneliness to the search for extraterrestrial intelligence. For decades, we've pointed our most sensitive instruments toward the stars, listening for signals that never come. We've searched for signs of massive engineering projects, Dyson spheres, stellar engines, megastructures that could reshape entire star systems. We've looked for chemical biosignatures in the atmospheres of distant planets. The silence has been deafening. No radio messages, no optical pulses, no obviously artificial structures, no sister civilizations calling across the void to say, "You are not alone. We are here. Welcome to the galactic community." This silence forces us to confront uncomfortable possibilities. Maybe intelligence is vanishingly rare, and we're essentially alone in a galaxy of lifeless rocks. Maybe intelligence is common, but technological civilizations inevitably destroy themselves before achieving interstellar communication. Maybe the distances are simply too vast, the timescales too long, for communication to occur between civilizations separated by thousands of light years and millions of years. Or maybe, just maybe, they're here, but hiding, watching, waiting. The possibility that 3I/ATLAS might represent artificial technology transforms the emotional landscape of the search. It changes the question from "where is everyone?" to "what if they're already here, but we can't see them?" The idea is simultaneously thrilling and terrifying. Thrilling because it means we're not alone, that the universe contains other minds, other perspectives, other ways of being intelligent. Terrifying because it means we're being observed without our knowledge, studied like bacteria in a petri dish, subjects of an experiment we didn't consent to join. Dr. Diana Pasulka, professor of religious studies at the University of North Carolina and author of American Cosmic, notes the quasi-religious dimensions of the 3I/ATLAS phenomenon. Throughout human history, we've told stories about watchers from above, gods, angels, spirits observing humanity from the heavens. Pasulka observes. The possibility that interstellar probes might be quietly observing us taps into these ancient psychological patterns. It transforms space exploration from a purely scientific endeavor into something approaching a spiritual quest. This spiritual dimension manifests in the language surrounding 3I/ATLAS. The object is described as a visitor, a messenger, an emissary, terms laden with intention and purpose. Its trajectory is choreographed, designed, planned, words that imply intelligence and agency. Even skeptics who firmly believe in natural origins find themselves drawn into the narrative, forced to grapple with the emotional weight of what confirmation would mean. The weight of uncertainty. As October 2025 approaches in 3I/ATLAS reaches perihelion, humanity stands at a crossroads of knowledge and uncertainty. The object will either develop normal cometary activity, resolving the mystery in favor of natural origins, or it will remain silent, deepening the enigma and strengthening arguments for extraordinary explanations. But even resolution may not bring certainty. If cometary activity appears, questions will remain. Is it genuine natural outgassing or sophisticated mimicry designed to allay suspicion? If the gases detected show unusual composition or geometric patterns, will that constitute evidence of artificial systems or merely unusual natural processes? If no activity appears, if 3I/ATLAS passes through perihelion, completely inert, the scientific community will face its greatest challenge yet. How do we explain a 7-mile-wide object composed of ice that doesn't sublimate under intense solar heating? What natural mechanism could produce such behavior? The absence of cometary activity would force consideration of exotic explanations. Unusual molecular structures that resist sublimation, surface layers of insulating material preventing heat penetration, exotic ice compositions that sublime at temperatures different from those expected, or, most provocatively, artificial construction designed to resist thermal decomposition. Each explanation carries implications that extend far beyond 3I/ATLAS itself. The coming months will test not just our technology and scientific methods, but our philosophical frameworks for understanding evidence and evaluating extraordinary claims. We live in an era of unprecedented capability for detecting and analyzing cosmic visitors. Our telescopes can resolve surface features on objects millions of miles away. Our spectrometers can detect trace molecules at parts per billion concentrations. Our computational models can simulate complex gravitational interactions with extraordinary precision. Yet we remain fundamentally limited by our imagination and preconceptions. We can only recognize what we know to look for. We can only interpret observations through the lens of our existing theories. We can only evaluate possibilities we can conceive. What if 3I/ATLAS represents something we haven't imagined? Not quite artificial, not quite natural, but something that transcends these human categories? What if it's a form of intelligence so alien that our biological minds literally cannot comprehend it? These questions have no answers, only the perpetual invitation to wonder, to question, to remain open to possibilities that challenge our assumptions about reality. The meditation. Picture 3I/ATLAS in your mind now. 7 miles wide, older than Earth, composed of ice that formed around a star whose light has long since faded from the sky. It's moving through space at 33 kilometers per second, 74,000 miles per hour. Yet from our perspective, it seems to glide serenely through the darkness, patient and eternal. Right now, as you contemplate these words, it's passing Mars. The red planet's rusty surface reflects faintly on its ancient ice. Perhaps, just perhaps, sensors aboard the object are analyzing that reflected light, cataloging another world, adding Mars to some cosmic database of planetary bodies. In 2 months, it will round the sun, experiencing heat for perhaps the first time in millions of years. The ice will warm, molecules will vibrate with increasing energy. The boundary between solid and gas will become permeable. What will happen in that moment? Will water vapor burst forth in jets and geysers, creating a magnificent coma that streams millions of miles into space? Proof that this is merely a comet, a natural relic, an ordinary visitor from an ordinary stellar system? Or will it remain silent, inert, mysterious? Its ice somehow immune to heat that should vaporize it, its surface somehow resistant to sublimation, its nature somehow beyond our categories of understanding. By spring, it will thread through Jupiter's magnetosphere, passing through radiation that would sterilize any unshielded life, that would fry any unprotected electronics. And then, it will leave, moving back out into the dark between stars, carrying whatever data it collected, whatever observations it made, whatever conclusions it reached about this small blue world orbiting an unremarkable yellow star. We will watch it fade, first from amateur telescopes, then from professional instruments, then from even our most powerful observatories. It will become invisible, but not gone, still traveling, still moving through space, still carrying its secrets into the cosmic night. Perhaps decades from now, it will pass another star system. Perhaps sensors aboard it, if such exist, will study that system as carefully as it studied ours. Perhaps another civilization will detect it, debate its nature, wonder if they're alone. Or perhaps it will wander forever through the empty spaces between stars, eternal and patient, one more silent witness to the universe's vast indifference. The final reflection. The story of 3I/ATLAS is ultimately a story about ourselves. It's about our hunger for connection in a vast and lonely universe. It's about our tendency to see patterns and meaning in random events. It's about the tension between skepticism and wonder, between the desire for extraordinary discoveries and the need for rigorous evidence. It's about the fact that we are a species that looks up at the night sky and asks, who else is out there? Are we alone? Is anyone watching? These are ancient questions, asked by every culture throughout human history. Our ancestors looked up at the same stars and wondered if gods lived among them. They saw patterns in the constellations and wove myths to explain them. They watched meteors streak across the sky and imagined divine messages or cosmic battles. We do the same thing today, just with more sophisticated tools and more complex theories. We see an object moving through our solar system on an improbable trajectory, and we wonder, could this be them? Could this be first contact? Could this be proof that we're not alone? Maybe it is. Maybe 3I/ATLAS really does represent an artificial object sent by an advanced civilization to study our solar system. Maybe we're being observed right now by intelligence so far beyond ours that we're like insects to them. Interesting perhaps, but ultimately incomprehensible in our limitations. Or maybe it's just a comet, just ice and rock and organic molecules that happen to form around another star, happen to get ejected into interstellar space, happen to follow a trajectory that brought it through our solar system, happen to align with our planets in ways that seem designed but are merely coincidental. Both possibilities inspire awe. If it's artificial, we're not alone. We live in a universe populated by other minds, other civilizations, other ways of being intelligent. The cosmos is not a dead clockwork mechanism, but a garden teeming with life and consciousness. If it's natural, we're witnessing a miracle of cosmic chance. Of all the possible trajectories through infinite space, this object happened to pass through our tiny corner of the galaxy at precisely the moment when we developed the technology to detect it. We're connected through physics and chemistry to stellar systems light years away, all of us products of the same cosmic processes that turn hydrogen into stars, stars into heavy elements, and heavy elements into planets and life. Either way, we're part of something vast and beautiful and mysterious. The search for answers about 3I/ATLAS is really a search for answers about ourselves. Who are we? Where do we come from? Where are we going? Are we alone? Does our existence mean anything in the context of cosmic time and space? These questions have no final answers, only the perpetual process of asking, investigating, wondering. Science at its best is not about certainty, but about curiosity. Not about final answers, but about better questions. Not about closing mysteries, but about opening our minds to possibilities we hadn't imagined. 3I/ATLAS, whether natural or artificial, whether ordinary or extraordinary, has already given us a tremendous gift. It has reminded us that the universe is still full of surprises. That space is not empty, but populated by travelers from distant worlds. That our solar system is not an isolated island, but a waypoint on ancient routes that connect the stars. It has forced us to confront the limitations of our knowledge and the breadth of our ignorance. It has challenged our assumptions about what's possible and what's probable. It has sparked debates that sharpen our thinking and refined our methods for evaluating evidence. Most importantly, it has invited us to wonder, to look up at the night sky not with fear or indifference, but with curiosity and hope. To imagine that somewhere out there, among the billions of stars and billions of galaxies, other minds might be looking up at their skies, asking the same questions, wondering if they're alone. The true mystery isn't whether 3I/ATLAS is watching us. The true mystery is that we're capable of asking the question at all, that we, products of 13.8 billion years of cosmic evolution, assembled from atoms forged in the hearts of long-dead stars, can contemplate our place in the universe and wonder about the existence of others like us. That capacity for wonder, that hunger for knowledge, that refusal to accept easy answers, that's what makes us human. That's what drives us to build telescopes and spacecraft, to search for signals from the stars, to study mysterious visitors that pass through our solar system. And whether 3I/ATLAS is a comet or a probe, whether it's natural or artificial, whether we're alone or observed, that sense of wonder, that cosmic curiosity, will continue to drive us forward, into the unknown, into the darkness between stars, into the eternal mystery that surrounds us on all sides. Are we alone in the universe? We don't know yet. But we're looking, we're listening, we're watching the skies, and one day, perhaps tomorrow, perhaps centuries from now, we may finally have our answer. Until then, we keep searching, We keep wondering, we keep asking, is anyone out there? And maybe, just maybe, somewhere in the cosmic dark, something is asking the same question about us.